Es sagt Low Battery, aber es wird hoffentlich. Okay. Mhm.
All right. Good morning, everyone. Welcome to the last day of this workshop. So the first speaker this morning is Thorsten Heidersdorf, and he will tell us some recent results on representation theory of algebraic supergroups.
Yeah, so thanks a lot for the invitation. So I decided not to present maybe one technical theorem. I would rather like to give some kind of survey talk about some of the things that happened in the representation theory of supergroups. This will be a very biased survey, so I'll try to squeeze my name in quite often, and I will ignore many other results which were relevant. So my excuses to people that are maybe swept under the rug right now. So this is the setup. So I take a Lie superalgebra over the complex numbers. I will only look at finite dimensional Lie superalgebras, and so here are some examples. They are in fact all simple. So there is SLMN. If M is equal to N, that's not simple, but you can take a quotient PSLNN. Then there is the autosymplectic Lie superalgebra. And then there are two strange ones. That's actually their proper name. They're called strange PN, periplectic, and QN, the queer Lie superalgebra. Then there are some exceptional Lie superalgebras, and then there are Lie superalgebras of Cartan type. And so the classification of Katz in the 70s said that these are all simple finite dimensional Lie superalgebras over the complex numbers. And for the sake of this talk, I will mostly, most of it will be here about this type A case, and I will actually mostly talk about GLMN. But if you understand GLMN, you understand the others. I will completely basically ignore the last two here, the exceptional ones and the ones of Cartan type. And the reason that I ignore the exceptional ones is the following. So this representation theory of, so the biggest difference of representations of Lie superalgebras versus representation theory of semi-simple Lie algebras is that the representation categories are basically never semi-simple. There's only one case here, the OSP1-2N case, which has semi-simple representation category, but you can somehow measure the failure of semi-simplicity of these categories by something called the defect or atypicality. The exceptional Lie superalgebras have defect 1, so they're pretty close to semi-simple, and you can work out most questions in a brute force ad hoc way. And so from a representation theory point of view, they're not so interesting. Most of the questions that I will talk about today were settled longer ago. And I will ignore the ones of Cartan type because I just don't know anything about them, and they have rather weird representation theories. Okay, so I'm going to look at finite dimensional representations of these on supervector spaces. So if I have a supervector space, there's a Lie superalgebra GLV, where the supercommutator just gives you this bracket that you need for the Lie algebra structure. And in fact, I inserted a warning here. I will actually work with some full subcategory, namely I will only consider representations which integrate to the algebraic supergroup, so integrable representations. So that's a setup, and so basically the question is, what do we know about these finite dimensional representations? And so there's a lot of early work by Katz in the 70s. So for instance, he classified finite dimensional irreducible representations in terms of highest weights, pretty much similar to the classical theory. There are some difficulties there that Borels are not conjugate and so on, so which means that you have to sort of fix a Borel and then you can determine which weights lead to, I mean, what is the condition for a weight to be dominant integral, and all this gets a bit messy, but I will ignore this. But yeah, so there is such a classification of finite dimensional irreducible representations. And he also, so once you have a finite dimensional irreducible representation, you can talk about its character, which is defined as in the classical case. So these have weight-space decompositions. So you can take the formal sum, dim, say L lambda mu, so the mu weight space of L lambda, and then e to the mu, and you can ask, is there a closed formula? A nice formula like the Weil character formula. And so Katz was able to obtain some character formulas, but it depended on the weight lambda. So what we'll see is that somehow that this failure of semi-simplicity makes the character problem to a very challenging problem because you don't have somehow direct construction of the irreducibles. And so Katz solved this for so-called typical weights. And so yeah, here's that one statement that I mentioned before. So rep-G is semi-simple. Well, okay, I made a mistake here because I talk only about algebraic representations, so let me correct this. That's very convenient that I have this G reductive. Or G is OSP 1 to n. And so that renders many tools from classical Lie theory useless. And so the questions that I want to consider today are the following. So first of all, you can look at rep-G just as an abelian category. So you can ask, okay, what are the indecomposable objects? How many are there? Can I construct all of them? If this category is not semi-simple, this is caused by irreducible representations having extensions. So what are the possible extensions? These kinds of things, or what are endomorphism algebras of maybe projective covers, all kinds of things. The second question is very simple. What is the dimension of an irreducible module? So for the classical case, there's the Weil dimension formula, which you readily get from the character formula just by taking some limit. But we just saw that the character problem isn't so easy, so it's not completely clear that you can do this. Then you can ask for the superdimension. So these are representations are super vector spaces with a G action. So for a super vector space, you can take the superdimension, dimension of the even part, minus dimension of the odd part. And then you can ask, what is the character? Is there a nice formula? Then you can ask, well, what are the fusion rules? So if I take two irreducible representations, I can tensor them together, and I can try to decompose it. And the lack of semi-simplicity will mean that, unlike in the classical case where this is always completely reducible, this will only decompose into some indecomposable representations. And you can ask, okay, which indecomposable representations come up, with what multiplicity, and so on. And the last question that you might ask, what are branching laws? When you embed some subgroup and you restrict, and how does it split? And in fact, the branching laws, I mean, the fifth problem is actually a special case of the sixth. And so what is the status? I basically gave you the answers here, and I will try to basically explain the answers that I gave here. I think I forgot, well, so the answer to one is mostly okay. So mostly okay means the following. First of all, in general, you cannot classify the indecomposables of these categories. There are just too many. Technical term is wild representation type. But people worked out precisely when this happens, when you have when you can classify the indecomposables and when you cannot. If you go back to the list here, so if you take SLMN and either M or N is 1, then you have so-called tame representation type, and there is a classification of the indecomposables. But as soon as M and N are both bigger than 2, you cannot classify the indecomposables anymore. And similar things happen for OSP, Pn, and Qn. The exception always have tame representation type, and people have worked out a complete list of indecomposable representations. And if you look at, so what do I mean then with mostly okay for OSP and GLN and so on? Well, so for GLMN and OSPM to N, I think you have as much control as you can possibly hope about these questions like X1 or how do I construct intercomposables. So for instance, there's a complete description when irreducibles have extensions and so on and so on. I'll talk about this a bit later. This mostly work due to Brandon Stroppel and Erik and Stroppel. So then the dimension of the irreducibles. So yeah, I mean, for most cases we have dimension formulas, but they are mostly pretty bad. So they are, I mean, they are after all explicit, so you can put it on a computer and the computer will do it for you, but you don't want to work with them often. Theoretically, they are ugly and certainly not optimal. So that's true for GLMN, OSPM to N, QN. I think for PN it's open, that's the only open case. The superdimension problem is much easier. Some of the superdimension seems to be the right analog of the dimension here in the superworld. So in that case, I think we have a complete solution. I'll talk about this a bit later. Character formulas, well, character formulas are mostly known. The one exception is again Pn, in which case we have some kind of infinite character formula. For the others, we have finite character formulas, but they are again often not very pretty, but it's getting better and better. And of course, somehow the answer 2 basically comes from answering question 4, because you can take again some limit, evaluate this character and get the dimension formulas. But the problem is that these characters have sort of alternating signs, which doesn't matter too much for the character formula, but then when you sort of evaluate this limit, you get some dimension formulas which have lots of alternating terms, and that is something you don't want in a dimension formula.
Is it the superdimensioned signs?
Mm-hmm.
Is the signs corresponding to the superdimension instead of the dimension?
Well, I mean, no. The signs come from, so one easy case how signs can arise is that no, essentially they have nothing to do with the superdimensions, the signs that come up. Because if you take a, let's say, character formula, you really just take the formal sum over the dimensions of the weight spaces. So you're not looking at superdimensions of weight spaces. You can also take the super character, in which case you, but that's not the one you would that's not the one you would use to get dimension formulas. You would take the super character to get the super dimensions. Yeah. And in fact, in that case, you have nice cancellations, and you could use the super character formulas to get super dimensions. That's one way to get it. But the signs in the character formula have sort of different origin.
Right. Okay. So the super character is probably nicer in some sense?
Yes, it's often nicer. But okay, well, okay, I want to withdraw the answer. It depends on the group that you consider. So for GLMN and OSP, M2N, the super character and the character are actually almost the same. So it turns out that for those Lie superalgebras, the dimension of, so weight spaces are either purely even or purely odd. So it means whether you take the dimension of a weight space or the super dimension of a weight space doesn't really matter. They're the same up to a minus sign, plus minus sign. So that means when you take the character or super character formula, they're basically the same up to sign factors that appear there. So if you know one, you know the other. And that's, for instance, not true for QN. For QN, weight spaces always have the same even and odd dimension, so the super dimension of every weight space vanishes. So it means that actually for QN, the super character completely identically vanishes for every irreducible representation,
so
except the
there's
trivial.
There's no consistent grading
Yes.
in white space. Yeah.
Yeah, I mean, yes, exactly. Yeah, yeah. So weight space are yeah. So the dimension of the even part is exactly the dimension of the odd part. And so that means that for Qn, the super character vanishes, but the character is highly non-trivial. Okay, so yeah, then fusion rules. Yeah, that's really a difficult case. And here we only know special cases. I will talk mostly about GLMN, where we have partial results, and they're partial results for OSP, but beyond that, I think this is unexplored and very difficult. And then I won't even talk about branching laws. I think that unless you take extremely special representations, like, I don't know, standard representation or so, we don't know what happens when you restrict to certain subgroups. I mean, so sometimes low-ranked cases were worked out, like SL21, and you bet in SL11 into SL21. These kinds of things might be known, but there are no general formulas at all. Okay, so let's focus maybe on in the beginning on GLMN. So here's just a brief reminder. I mean, I think GLMN, SLMN came up frequently, so maybe this is a bit. So I will be very brief. So these are all endomorphisms of this super vector space CMN, where I just view this here as even and this here as odd. And then if you choose a basis in the usual way, and then you can identify these endomorphisms of matrices. There they are. These are block matrices. And the bracket is given by the super commutator. So here you have these, so X, the symbols mean the following. You take a homogeneous X and a homogeneous Y. So homogeneous means either purely even or purely odd. And if it's purely even, you say the parity is 0, and if it's odd, you say the parity is 1, and that defines this X and this parities here, and then you extend linearly. So that's the super commutator that turns it into a Lie superalgebra. And maybe the first thing you want to do when you try to understand representations, you want to use the even subalgebra, which is given here by these block matrices AD, and it's just GLM cross GLN. And then you can start with an irreducible representation of this even subalgebra, and you can induce it. So first you extend to this parabolic, to this ABD matrices, and then you induct. And you get something finite dimensional in this way. This is called K lambda in honor of Katz. So it's called the Katz module. And this has a simple top. So it has a unique maximal submodule. When you mod out the submodule, you keep an irreducible module. That's a simple module of weight lambda. So the lambda here, when I started, was weight for GLM cross GLN. And so for each dominant integral weight of GLM cross GLN, I end up with a simple representation L lambda of GLMN. So in that way, I've produced lots of irreducible representations. And now this module might be simple or might not be simple, and you can very nicely characterize when this happens in terms of the weight. So there are conditions on the coefficients. And if it's simple, then you call this weight typical. And the name is well chosen because most weights are typical. If you would draw the weight lattice, somehow the ones that are not typical are somehow a thin subset. And so the slogan is that these typical weights are the good weights. They don't cause problems. And the whole failure of semi-simplicity is due to these atypical weights. So if every weight was typical, then the category would be semi-simple.
So if you take the kind of representations we're used to in physics, tensorial representations of fundamental or vector-like.
Yeah, they're typical. Well, no, they're not always typical. Well, okay, so if you take polynomial representations of GLMN, they're not always typical, but still V tensor R, so where V is the standard representation, is completely reducible.
Maybe from the off as a physicist, I mean, this would be in physics notion sort of short multiplets. So if you have extra shortening conditions, that's what you get, what you call atypical in mathematics.
So what is the question?
Are these tensor, graded symmetric tensors, are they typical or atypical?
So you mean like something like sum of something of a standard or exterior powers of standard representations? No, they're not necessarily typical. No. Actually, I'll say a little bit about this. Yeah. Okay, and so otherwise you call them atypical. And so I think I didn't write it. No, I didn't write it on the slides, but for instance, if you take now GLMN, you can prove that L lambda is projective, so it doesn't admit any extensions if and only if it's typical. So in that sense, really, they are the atypical weights are responsible for the failure of semi-simplicity. Okay, let's continue with GLMN, and so I'm going to introduce some graphical calculus, which is due to Brandon and Stoppel. I think it has become clear in the last 10 years that in order to understand these L lambdas and their properties, you should forget about the sort of the usual way to write dominant integral weights. So here, what you see on the right-hand side up here, these are basically dominant integral weights for GLM cross GLM. These are just integer entries, and they are arranged by size for these two parts. So this is somehow the GLM part, and this is the GLN part. And this gives you all irreducible representations up to parity shift. So when you have a representation, you can always replace it by its parity shift, where you just flip the even and the odd part of the supervector space. And they're not isomorphic if you only allow even morphisms. So you basically get two irreducible representations in this way. And so what I would like to do is I would try to forget this way of writing dominant integral weights. I want to attach to it something like a weight diagram and work with this weight diagram. And so here's how it works. You define two finite subsets, one of cardinality M, the other of cardinality N. And you see, you just take basically the coefficients and you shift it a little bit. And the shift is sort of irrelevant. It's only you want to now label the number line Z with certain symbols. And you might, of course, have lambda 1 here equal to lambda 2 or something like this. And I don't want two symbols on the same position in the number line. That's why I introduce these shifts. Okay, and now I label my number line. So if I have something intersection, I label it by this down. Then there are finitely many remaining in this IX and I naught. So I label them by a cross or by a naught. And all others, all infinitely many others, I label by an up.
Sorry, a stupid question again. These lambdas are not Lincoln labels. They are lengths of things in some Young tableau. What are they?
Yeah, so I mean, what I take is, so I mean, if I take such a matrix, I have the obvious diagonal matrices inside. And then I take some of the standard basis of these diagonal matrices. I just take epsilon I and I evaluate on the j's. I just take so epsilon I takes the i's term of the diagonal entry, and that's what it gives.
Nothing like fundamental weights or...
No, these are not fundamental weights. No. And then, so I write my, so I write my lambda in terms of these basis vectors. Lambda I, epsilon I, and this is maybe from 1 to m. And then I have okay, this was. And yeah, these epsilons are the obvious basis functions on the diagonal matrices, which give me my Cartan subalgebra. And that's what you see.
Sorry, I have a question. Okay, when you actually you talk about the supervector space, then you say that you can shift. I mean, you can change the parity. So you
yes.
Can, okay, but can you remind me what happened if there is this metapletic representation? Were there are such representation in this case? So if you shift from, I mean, if you change the supervector space, the parity of supervector space, you don't create this metapletic representation? Or I'm wrong? Probably I'm wrong.
These representations are finite dimensional, and the metapletic group doesn't have interesting finite dimension.
Oh, that's right. All infinite dimensional representation. Okay.
Except the
okay.
dimension.
Okay. Thank you.
Okay, so here I just drew a picture of how this might look. It's a weight diagram. Of course, it goes infinitely to the left and the right. And so here you see finitely many of these downs. There are a finite number of these crosses and knots, and all the others are these ups. That's how this weight diagram looks, and the weight diagram uniquely determines the weight. You can retranslate. Okay, and now when I take this weight diagram, I want to attach caps. So I go from the right to the left through this weight diagram. So let's do it here. And so what I do is I always connect downs with ups, and I connect a down with the next up, next free available up to the right. So if I'm here, oops, I join. Oops, so this was wrong. I join these here. Then this was wrong. Then I join these here. I join this here. This here. Now here I have to jump here. And so on. And okay, here I have to draw this huge cap. Okay. And somehow this seems to be the right way to express many properties of these weights. So I'll talk about some later on, but for instance, you can very nicely express the superdimension of L lambda in terms of some of the structure of these cap diagrams. I'll make a precise statement later. But for instance, you can also study the effect of translation functors on simples. So translation functors means the following. You have the standard representation or its dual. You tensor your irreducible representation with the standard representation, and you project somehow to some, say, eigenspace of a Casimir or whatever. And you want to know what happens to this irreducible representation, how does it transform. And you can very nicely express this typically in such a diagram, because essentially it means like moving, you take some position here in your diagram, and it just means you flip the two. Something like this. And so this is a very convenient way to express such translation functors. If you want to know, for instance, what are the possible x1 between two irreducible modules, so first of all, if the two irreducible modules don't have the same positions of the crosses and the knots, they are never extensions. So in mathematical terms, these crosses and the knots, they determine the block of the irreducible representation. And so let's take two representations with the same labeling of crosses and knots, and then you can transform your irreducible representation the following way. You can take such a cap, and then you see it always has this down on one side and an up on the other side. And now you can flip the two. It means that you just shift this here, and you shift this here. And it gives you a new weight, a weight diagram of a new weight. And the statement is you have a non-trivial x1 between two irreducibles, either if and only if one is obtained from the other by such a switch in one of the caps. You are only allowed to switch one cap. You know? And so, and you look at this weight diagram or this cap diagram. For instance, here, if you express this again in terms of these lambda i's, you don't see anything. You don't see any rule because you have these huge switches. And so this seems to be, such a structure seems to be invisible if you just write this as a sum of these lambda i's. Okay, so let me just mention, and I will be extremely brief, that there's some theory behind it, and I don't think it's really suited right now, but so what is behind it is a theory of Brannan and Stropel of so-called Kovanov algebras. So what I mean is the following. So you can split your category rep GLMN into so-called blocks. You look at, you check when two irreducible modules can have sort of iterated extensions. This defines an equivalence relation on the set of irreducible representations, and you look at all the intercomposite modules that you can form with an equivalence class of irreducible representations. That gives you this block decomposition. And then you take, you define the so-called locally finite endomorphism algebra, which are called n-fin p gamma, where you just sum up of all these HOMs between these p lambda i's and p mu j's. So these are projective covers. So remember, the category is not semi-simple, but it has enough projectives. That's what Vera gave an argument yesterday for this. So that's the projective cover, and you can look at the homomorphisms between this, and you sum up over this. And then you can look, this is an algebra, and you can look at modules over this algebra. And this equivalent as an abelian category to this block that you started with. This is just abstract nonsense. You can always do this in case you have something like a projective generator or something like an analog like this. So it seems it gives you a new way to think about this gamma or these subcategories, but in general, this is in this way it's completely useless because I mean describing this modules over this locally finite endomorphism algebra is as difficult as describing gamma. You just shifted the viewpoint, but you didn't gain anything. But the punchline is, and this goes back to Brandenstoppel, that in fact in this case you can describe this algebra completely explicitly. It's a certain diagrammatic algebra, which they call a Kovanov algebra of type A. It's a diagrammatic algebra. Maybe you've seen something like a Temperley-Lieb algebra or a Bauer algebra. So these are algebras which are defined by some kind of planar calculus. And this is one of them, just much more complicated. And you can completely explicitly describe this algebra and its modules. And this language of weight diagrams comes from this planar or diagrammatic calculus. So there's a big theory behind it, but for my talk, I'll just use this ad hoc. I just use it as a very convenient way to express things about these L lambda. Yeah, so the slogan is somehow that the complexity of these cap diagrams measures how complicated L lambda is. So here's, for instance, one property. If you don't have any downs, then the weight is typical. Weight is typical if and only if there are no downs. And this is the case if and only if L lambda is projective. If you have one down, then it's called one atypical. If you have two downs, it's called two atypical, and so on. You can have at most minimum of M and N downs. So, and somehow this atypicality is a measure for the difficulty of this weight L lambda, how far it is off from being semi-simple. And so, for instance, if you, so I said you can have at most as many downs as the minimum of M and N. So, for instance, if you take GLM1, and for some reason I switched to the group, but I hope that doesn't cause confusions. So for instance, if you're in GLM1, you can have either no downs or one down. So you can have either typical weights or one atypical weights. So here are weights which are very, very good, very convenient. So here's another example of a weight, a cap diagram. It takes these weights which are k, 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 minus k, and so on. So this is called the case tensor power of the Berezinian. It's some kind of analog of a determinant power in the setting. And here you see the associated cap diagram. So this has high atypicality, maximal atypicality in fact, but it's still an easy weight because somehow its cap diagram has this easy symmetric structure. So well, this is a very special case because you don't even have crosses or knots. But in general, because of the importance in the theory, if you have weights which have these completely nested cap diagrams, they get a special name. They're called constant weights. And so they're also good in the sense that while they may be highly atypical, we basically understand them very well. And so sometimes many proofs will use some kind of reduction to these weights. So as I said, they're called constant weights. So for instance, a typical or one atypical weight is automatically a constant weight. And so one way in which they naturally occur is if you take the standard representation, or the natural representation, and you take its tensor powers, and then you decompose it. And there's a little miracle here. This is completely reducible. So there's very, very few things that are completely reducible in this world, but tensor powers of the natural representations are among them. And so a long time ago, by results by Berle, Regev, and Sergeyev, these irreducible representations were determined that come up in this way, and they're all constant weights. But not every constant weight comes up as some irreducible summand. And you can strengthen this result, so you can look at mixed tensor powers. So the natural representation is not self-dual, and so you can look at this mixed tensor space. You take an R tensor power of the natural representation and an S tensor power of its dual. This is not semi-simple, it's not completely reducible, but in fact the indecomposable representations that come up, they can be classified, and we basically know everything about them. So we know the dimension, the very nice dimension formulas, we know their characters, we know even the tensor product decomposition between those is known. You can explicitly write down the composition factors or whatever you like about these indecomposable modules. But the drawback is all irreducible representations arising in this way, some summoned in some of this, in some mixed tensor space, they're always constant weights. So you only get these sort of easy cap diagrams. And so if you can ask, okay, I mean, how restrictive is this? And it's extremely restrictive. So if you take a weight, say of atypicality k, how do you define this basically? Well, it means you distribute k down somewhere on the number line, anywhere you like. And I mean, so it means that sort of this constant weights basically are very special, because it would mean you'd sort of put all the downs basically next to each other to get something like this. And you see the difference to the classical theory, because if you would take this mixed tensor space for GLN, you would get every irreducible representation in this way. But here you basically only get these constant weights. I should say there's something missing here. In fact, you can prove basically every constant weight occurs in this way. If you take mixed tensor powers up to some shift of this Bayesian representation that I wrote down. Okay, so that's GLMN. I think the slogan for GLMN, if I summarize, is that we understand the mixed tensor powers right now, but nothing else. You can move to the OSP case, and here I wrote actually the group on purpose because, well, there's the Lie superalgebra OSP, and the representation theory of this Lie superalgebra is the same as the representation theory of the algebraic supergroup SOSP, so the connected component of this OSP. But for it is quite, it's a lot more convenient to work with the group OSP than with SOSP, because this is, well, you have to otherwise worry about restricting to the connected component, and then things can decompose and things like this. Okay, so let me just be brief and say there is an explicit description of this endomorphism algebra of some kind of projective generator. This is due to Erich Stroppel. So you have the same diagrammatic calculus, just a bit more complicated. You can again define weight and cap diagrams. So people came up with slightly different notation, but otherwise this is morally the same. There are some differences. So sometimes in order to distinguish two weights, you have to add a sign to the weight diagram. And these weight diagrams have a minimal element always. So a minimal, so we're only looking here at n, the positive integers. That comes from the condition that weights are dominant integral for OSP. So it means these are minimal elements. So you cannot take the lambda i's to be negative as for GLMN. So there is, it's a cutoff here. And so if you're at the 0 position, you allow, and you have atypical symbols at the 0 position, you can stack them. You can also introduce some variants where you transport them somewhere here, but yeah. But otherwise, you have a weight diagram calculus, you have a cap diagram calculus. All things are pretty much similar. So here's a cap diagram, and there's one special rule that if you have one of these stacked symbols at the origin, then sort of your cap has two arcs. You connect it to the next, so you connect it here and here. It counts as one cap, but it has sort of two ends. But otherwise, these cap diagrams serve the same purpose as for GLMN. So again, you can express X1s, translation functors, or whatever you like in terms of these diagrams. And let me just mention on the side that you can also introduce some diagrammatic calculus for Pn and Qn, but there's no analog, so this is sort of ad hoc. It's just a way of thinking about this it's just a combinatorial tool. There's right now no analog of this Kovanov algebras that control everything. I mean, people are trying to get there, but it's kind of complicated. So the analog of the mixed tensor space here is just, you take the natural representation, so V is just C to the M 2N, and take its tensor powers. So there's no sense talking about mixed tensor powers because V is self-dual. This is not completely reducible, but as for GLMN, you can classify the indecomposable summons and you can determine the fusion rules. So very recently, even unpublished, you can also describe these indecomposable summons that occur in this way explicitly and do whatever you like with them. Like for GLMN, this was recent work by Nehme. It was a master's thesis that was just handed in September. But what you see, even in this case, if you look at the irreducible summons that come up in such a tensor power, they're again constant weights, where constant could be defined as for GLMN. This just means completely nested cup diagram. So again, very, very special. And so we again in the stupid situation that we don't, we understand these constant modules, but nothing else. Okay, so I want to say a few words about character formulas. And I just noticed that I blathered a bit too much, so I have to speed up a bit. So as I said, for typical weights, cuts prove the character formula. That's the one here. This R is the so-called Weil denominator. It's independent of lambda. This is the so-called Weil vector here. And then, so the essential part is this one here. And it looks pretty much like a Weil character formula in the classical case. And then GLN1 was treated by Bernstein, Leites, and van der Joy, Kings. I forgot the list of people, but there were a couple of people, mostly from math physics, that proved this character formula here. But then, so this is sort of the one atypical case. This is note, these are called constant modules. So this is also covered by the general theory nowadays. But beyond that, little was known for a long time. Then in the mid-90s, Saganova wrote down some kind of infinite character formula in terms of these Katz modules. So for these Katz modules that I find in the beginning, you can write down the character explicitly, and so you can show that every irreducible module has a resolution in terms of Katz modules, and you can count sort of the occurrences of these Katz modules and somehow invert, and this gives you some kind of character formula. And then over the years, people came up with finite character formulas, for instance, for GLMN, QN by Zhu and Zhang, but they're very, okay, this is on YouTube, I shouldn't say it like this, but they're very complicated formulas you don't want to work with. And then the only remaining case which is open, I think, is PN. For PN, you have a similar solution as Saganova's solution as for GLMN. So it means that there are, you can write down an infinite resolution by Katz modules, and you can determine the occurrences of these Katz modules. It gives you an infinite character formula. But as of now, there is no finite character formula for PN. And so here is the result I proved. It's actually from this year with Maria Gorelik. But this is for GLMN, and the OSP case had been treated previously by Gruson and Saganova. So there is a character formula which looks like this. It's a finite sum, and you sum up, so there's this BLL prime, so L prime runs over irreducible, in principle over all irreducible modules, but there's a finiteness condition built in, so it's a finite sum. And then KW for Katz-Wakimoto, because they considered those previously. So this has the following property. First of all, if you sort of get rid of this Weil denominator and this e to the rho, then this is actually a basis of your charactering. Secondly, if you take these coefficients into a matrix, there's a lower triangular matrix with integral entries, one's on the diagonal, and you can just turn it into a matrix with positive entries by multiplying the diagonal matrix with some signs on the diagonal. And so once you do this, so once you sort of adjust signs, these here, these BLL prime, they can be completely explicitly expressed in terms of this cap diagram combinatoric. So basically you have to see, you write down the cap diagram of L, the one of L prime, and you somehow can by some moves, you can move one to the other. and you count the number of ways you can do this. And what is a move, for instance? A move is what I told you, when you have a cap and you have a down on one side and an up on the other side, you can flip the two. And so you can move your weight. But this would be a move of weight 0. You can have sort of higher weight moves, where you have an external outer cup, which encloses some inner cups, and you can take some down and sort of move it in some way in the big arc. But whatever, I think the precise rule is not important. The important thing is there's a completely explicit rule. And so at the end, what you get is a finite sum with integral coefficients in terms of a basis of the character ring. So that's probably, well, it's subjective, but probably the nicest character formula for GLMN. And there's, so for instance, if you would take a constant weight, then in fact all this BLL prime would collapse. This would just be Kronecker deltas. So then the whole thing collapses. Again, so some of the complexity of the cap diagram, how these caps are nested inside each other, expresses how complicated the weight is. And well, one application of these character formulas is that indeed you can get dimension formulas for this. You can also get complete formulas for the G0 decomposition of any irreducible module in this way, but the formulas are really not pretty. So G0 decomposition means the following. You can take your L lambda and you can restrict to the even subalgebra. And this gives you a formula for the decomposition, for the branching laws, basically in this case. But the formulas are really, really, really not pretty. And you can do this uniformly for GLMN and OSPM2N. Yeah, so these are character formulas, and that's how you get dimensions. So I said in the beginning that the superdimension problem is really solved. You could actually use these character formulas to compute superdimensions because, as I said, the super character is more or less the same as a character. And then you can try to evaluate the super character to get superdimensions. But I guess there's a better solution to the superdimension problem, which uses some kind of BRST operators. And I think these X here that come up were discussed in various talks. So you take an odd X, which is nilpotent, so XX is 0. Yeah, this kind of nilpotent varieties. So here's one example. You take zeros everywhere and just a little 1. Or you could take several ones here on the anti-diagonal, would also work. Or you could, of course, take ones on the diagonal, would also work. Something like this. And so if you apply this, if you act with such an element on a representation twice, you get 0. That's this condition here. So you get 0, and so you can talk about the cohomology. You just take the kernel of X, modulo the image, and I call this dsx. So V here is some representation in rep G. And I call it ds because of Duflo-Saganova, who defined this first. Studied this maybe 15 years ago. If you apply this to the joint representation, so to G acting on itself, you see that Gx actually has a structure of a least superalgebra. And so in this way, Duflo and Saganova obtained a functor which goes from rep G to rep Gx. And it turns out, and this is quite surprising, that this is a symmetric monoidal functor, so it's compatible with the tensor structures on both. And you can determine this Gx explicitly. So it's, for instance, if you take GLMN, you get GLM minus Kn minus K for some K. And here, if you would take these elements up here, it would be the K would be the number of ones on the anti-diagonal or the diagonal. So if you take a single 1, you go to GLM minus 1, N minus 1. You go down in steps of 1. And if you take OSP, you have this OSP N minus 2K, 2N minus 2K. And again, you can, depending on which X you take, you go down in bigger or smaller steps. And so this is a very powerful tool to reduce questions to lower rank. I mean, classically, you would like maybe to use restriction functors or something like this, but we don't know anything about these. So these Duflo-Saganova functors sort of allow to reduce many problems somewhat to lower rank and try to understand problems inductively. And so if you, now, let's iterate this construction. So we go down in steps of 1. At some point, so I will assume here for simplicity that m is at least as big as n. So if you do it then n times, you end up in GL m minus n, n minus n. So you end up in something well known and classical. And so ultimately, you end up in rep GL m minus n. And so you want to know what happens to your representation that you start with. Can I determine it? Because, I mean, this is symmetric monoidal functor, it preserves super dimensions. So it means that if you can calculate what happens to a representation all the way down, you have a super dimension formula. Okay? If you can determine which irreducible or which isotypic or whatever representation of GLM minus n you get, you have a super dimension formula, because the dimension, you can just compute the dimension with the Weil dimension formula, and that's it. That's a super dimension. And so for that, you need to know what does this ds functor do on irreducibles. And so a couple of years ago, Weiser and myself proved a formula for dsx of L lambda. So here, the x is actually of rank 1 in the statement. So, and this is actually surprisingly semi-simple. So irreducible representation goes to a semi-simple representation. And these L lambda i's that come up in this formulas, they're obtained by removing a maximal arc from the diagram. So an arc is, or a cap is maximal if it's not enclosed by any other cap. So for instance, if you take a cap diagram like this, you see there are sort of 3 maximal caps. It gives you 3 summons. Now, these summons might come up with a parity shift. So the pi is this parity shift, and it sort of measures if lambda or lambda I have the same parity or not, modulo 2. So there's a completely explicit formula. And in particular, this ds of L lambda is semi-simple and multiplicity free. And well, so when you go down all the way to GLM minus n, you actually, if you start with an irreducible representation, you get an isotypic representation. You just have to count the number of times this irreducible representation appears. This is this number m lambda here. And well, we showed that, I mean, this was previously known due to Weissau, but we showed that this m lambda has a very explicit expression in terms of this cap diagram. You basically, what you do is you read a cap diagram. You view it as a tree by starting from the outermost cap and going inside. So here I have done the translation. So this here corresponds to this tree, and this here corresponds to this tree. And so the nesting structure of these caps gives you the tree. So the union of trees, in other words, it's a forest of planar rooted trees that you get. And then you can express this lambda, this number m lambda in the following way. You take the number of nodes of this forest, and you just take the factorial, and you divide by the so-called forest factorial, where you sort of, which is recursively defined by going through this tree, and then, for instance, here, and then counting how many nodes are there, and then multiplying all these numbers together. So that's this m lambda, the multiplicity of this isotypic representation is a number between 1 and n factorial. And then this gets multiplied with the dimension of this irreducible representation of GLM minus n, to which this L lambda is mapped. And so, for instance, if you have a constant weight, well, m lambda is 1 if and only if it's a constant weight. Okay, so this is a the super dimension formula, and now I want to basically skip this part here because I have something else that I want to treat. Let me just say that the whole theory can be done for OSP in a similar way, so the ds functor is there. It just, so again, ds of L lambda is semi-simple. Again, there's a completely explicit rule how to remove that the summons corresponds to to sort of maximal caps. Big difference is that there is a multiplicity edge which can be 1 or 2. So sometimes a summon comes up twice. It's no longer multiplicity free. And the rule, when this mi is 1 or 2 is quite involved, so I won't tell you. You have to, for instance, if you take some cap, you have to count sort of the number of empty positions between that and sort of the minimal position, and depending on whether it's even or odd, and whether you are in the OSP 2m plus 1 or OSP 2m case, you get either 1 or 2. But again, a completely explicit rule, and of course you can play the same game as for GLMN, you can go down all the way. So if you do this for if you do it for OSPM to n, you end up either in representations of the orthogonal group, or the symplectic group, or the orthosymplectic group 1 to n, which is semi-simple and for which we know the dimensions. And so again, you get the superdimensional formulas in this way. Let me just, as a warning, say for Pn, this ds over lambda is not always semi-simple, but you can still sort of, if you go down all the way, and for Pn you would end up just in supervector spaces, then of course you get something semi-simple, and you can count the number of composition factors, and you still get a superdimensional formula in the same way, so it can be again expressed in some kind of forced combinatorics, like for GLMN, like for OSPM to n. And for Qn, the problem is uninteresting because, as I said before, the superdimension vanishes always. Okay, last topic, fusion rules. So the big unknown. As I said, for GLMN, if you have constant weights, which includes, for instance, GLM1 completely, you have a closed formula. Similarly for OSPM to n, as long as these are modules that come up in some tensor power of the natural representation. Then there are some low-rank cases that, I mean, for instance, physics literature, you find fusion rules for SL21 or so. There's, for instance, so SL21, for instance, was done by Götz-Queller-Schomerus, and there's some, the special case PSL22 was treated. But beyond that, I think we don't know anything. So there's this short sentence here, character formulas don't help. First of all, character formulas will never see the decomposition into indecomposable summons, but you could hope that at least it gives you the composition factors. It shows you what happens on the level of Grothendieck groups. And I just made the claim that we have these nice character formulas now in terms of these basis functions on my charactering. But it is a complete mystery how to multiply two of these Katswaki-Moto terms and expand it in terms of Katswaki-Moto terms. So I have no clue what happens there. So character formulas seem completely useless. But the last thing I want to mention, there are somehow truncated fusion rules. Something I did in the last years with Weissauer. So you can calculate the tensor product up to superdimension 0. What I mean is, if the superdimension of L lambda and L mu is 0, which happens pretty often, and then we don't know anything about these decompositions. But if you take L lambda and L mu, which have non-vanishing superdimension, then you can basically do the following. You can just kill all your indecomposable modules of superdimension 0 from your category, and there's some categorical way to do it, and you end up, what you get is astonishing, not some stupid category nobody can say anything about, but you get again the representation category of some supergroup or supergroup scheme, but this time, this is semi-simple. And there aren't many semi-simple supergroups, right? There are reductive ones and OSP 1 to n. So whatever this group is, this mysterious group G red, it must be somehow some limit of either reductive groups or OSP 1 to n. And so the basically vague version, or first approximation of a theorem I proved with Weissauer is if I don't take the full category rep GLMN, but I only look at modules that come up in iterated tensor products of irreducible representations. So I tensor two irreducible representations, I pick up the indecomposable summons, I tensor them, and so on. I iterate. That defines a monoidal subcategory of rep GLMN, and I kill these indecomposables. Then this G red is can essentially be determined in terms of classical groups. Classical groups means like SLMN, SP, SO, orthogonal group, and so on. And so what does it mean in down-to-earth terms? It means the following. You take an L lambda, an irreducible representation. So this defines an irreducible representation of this G red. Now you do this for L lambda and L mu, and then you tensor these irreducible representations of G red together. Because it's semi-simple, it's going to decompose completely. And hopefully you understand these fusion rules for G red, which will be the case for GLMN because these are after all just classical groups. And then you can sort of lift this back to your original category, and you get a decomposition of L lambda tensor L mu. But because I've killed all the indecomposables of superdimension 0, this is a truncated fusion rule. I never see superdimension 0 summand. I only see non-zero superdimension. And these I nu here, of course, then might not be irreducible. There are some indecomposable summands which correspond uniquely to these L nus that come up in this decomposition. And so this is abstract nonsense. This is always true, whether you talk about GLMN or OSPM or PN or whatever. The big question is, can you determine this V lambda, V mu, G red explicitly? And if so, you basically get some truncated fusion rules. And so the answer is that yes, you can essentially almost completely determine G red for GLMN, and it's of the form GLM minus N times some group which I call HMN. This HMN is a subgroup of some infinite product of groups H lambda, and these H lambdas, these are classical groups, which we can basically determine, and we can exactly say, well, if you take L lambda, what irreducible representation of this big group it corresponds to. And so it means that when you take an L lambda, it has sort of a GLM minus N part, and it has this HMN part. So it corresponds to an external tensor product of a GLM minus N representation and an HMN representation. And so if you want to tensor these two together, it just means that the fusion rule will be a mixture of the fusion rule for GLM minus N, which is just the Littlewood-Richardson rule, and the fusion rule for this HMN up to superdimension 0. And so just to finish things off, here is an example. So I just listed a few groups for GL44. I use a shortcut notation here. I'm only looking here at weights which are highly symmetric. So where you see it's just mirrored with a minus sign. You might wonder why I'm looking at these special weights. Well, the answer is actually if you take GL44, a weight only has non-vanishing superdimension if it has this perfect symmetry here. And I just use this shortcut notation then. Lambda 1, lambda 2, lambda 3, lambda 4. And here I'm going to list a few small weights. And here you see the groups that appear. So these are these groups that are on the right-hand side of the theorem. Let me just go back. So there's always this GLM minus N factor. I'm ignoring it, okay? I'm just showing you these here. And you see these are classical groups for which we understand the fusion rules, of course. The C is for compact, so I'm stating the compact form here. And so there's a little very annoying drawback. So I said we can almost always determine the V lambdas and the H lambdas. For some weights we cannot. And so here this SO24 could also be some kind of semi-direct product of SL12 and something. So, but all the others are fine. And you see these very explicit classical groups emerging, and so it means that the tensor product decomposition for GL44 is up to superdimension 0 actually completely classical in terms of classical groups. So this is something that could be done in principle for other groups, but it's very hard actually to do it. So this is only known for GLMN. And some, I think, recently Saganova announced that she can do some sort of defect 1 groups, so small rank groups, exceptional supergroups. Okay, I think I've already run over time, so yeah, that's it.
Thank you very much. So please, any questions? So probably by shouting, microphones will work, but I can also pass on this.
So this technique where you deform the superalgebra by a square zero element x, this looks very much like what we do when we twist a supersymmetric field theory. Is there some kind of interpretation what happens to the representations once you do this, which kind of connects to twisting or something like that?
Well, I'm not very familiar with this twisting technique, so I can't answer the question.
What was the last sentence? I didn't understand.
So I was wondering if there is an interpretation of this technique which connects to the procedure of twisting.
This is twisting. This is a kind of twisting.
Yeah, sure.
This is called twisting. Yes, you go down. You introduce this additional x, and then physicists say, okay, VR is t cohomology, which is just what this ds x is. The observation, which is, I think, not made in physics by Duflo and Saganova, is that this procedure is a tensor functor, which is a very crucial observation. It's very simple to prove, but was not detected, and that's very important. So I think if you have something, you compute Feynman integrals and things like that. Yeah, you have tensors of certain fields whenever you make an explicit computation, and Feynman integral actually is a contraction. You have a huge tensor product over the space, so to speak. Yeah? The space is a space of all functions on it, and then some fields which are finite dimensional representations. You twist something infinite dimensional with finite dimensional fields which have values in the finite dimensional representation. If you do this, at the end, the Feynman integral is a contraction. It's a projection on one-dimensional representation. But the key observation, all these tensors appearing in the space of functions, the value fields and so on, you contract them by dualizing all this stuff. This is a tensor functor. This is very essential. So it factorizes, and if you produce these twistings, you can still keep information. And this information is very crucial. I think it's not so much observed or used in physics literature. And I think it's a very useful observation. It's very powerful in math and should be the same thing, should be relevant. For instance, when I became interested in this list was key for me. I should say this. You see SU2 and SU3, there's a U1 missing, which is coming from the Barracene. And what made me interested in this whole stuff is there a hidden way to explain the standard model? You see, you introduce Geo44 is the SU24. It's the conformal group for Minkowski space. And you see, if you have field theories on Minkowski space or boundaries of alias-5, which are compactifications of Minkowski space, which have values not in complex numbers, but in finite dimensional representations of the conformal. One of these especially. And you are dealing with these fields and compute Feynman integrals. What are you doing? You make contractions, and these contractions are tensor functors. So if you have certain energy ranges you are considering, well, these Feynman integrals have the property that terms where you evaluate that have superdimension 1 do not contribute. You know, this is a typical idea in physics. They have this point where everything comes together is a certain energy range, where you have cancellations. You have these miraculous cancellations between even and odd. And I think physicists often are interested in super representations of superdimension 0. Yeah. But you should be very careful. I think in certain energy ranges, it might be so that all even and odds seem to asymptotically cancel. If there is a field theory with this property, what remains is superdimension different from zero. And then this is the maximal atypical representation. The most important representation there is the one-dimensional representation. Because if we integrate, compute a Feynman integral, you get a value, which means you project this huge tensor product on the one-dimensional representation, which is maximal atypical. So you see what remains could be the as a different odd contributions from modules of superdimension theory could, at a very high energy level, could have vanishing properties asymptotically. And then what remains is you can approximate your complicated supercategory by this reductive, this quotient. And then the whole contraction theory reduces to classical group reductions, exactly by these groups, SU2, SU1, SU3, SU5, SP6, SU12, SU8, SU12, and perhaps an SO24. Which means it could be that these are extended in a hidden way, in an approximation of a category of super groups, that in a hidden way as a quotient category, these classical groups appear, the standard model appears as an approximation at a certain
at low energy.
Certain energy.
Okay, thank you. Other questions? We can continue over coffee, actually, because now we have coffee break, right? So we have timing. Let's come back at 11:15, and let us thank Thorsten Heidersdorf for his talk. Ich meine, der Unitaritätstext funktioniert halt nicht. Das ist ja das Argument gegeben, dass halt das Volumen von dem aber trotzdem als die unitären Darstellungen sind immer noch so we see you and we have your slides. So YouTube is running. All right, so welcome back. So our next speaker is Pavel Safronov. He will tell us about virtual fundamental classes and BV quantization from supersymmetric twists.
Thanks for the invitation, and sorry I couldn't have been there in person. So I wanted to talk about some joint work with Brian Williams, who is in the audience. And the work consists of two papers. One of them is an archive, and the other one is still in progress. So there's two keywords. There's BV quantization, that's in the first paper, and virtual fundamental classes, that's in the second paper. And the first paper has already appeared, and the second one is still work in progress. Okay, so basically what I want to explain in this talk is some rigorous models for various partition functions and Hilbert spaces in supersymmetric theories with enhanced supersymmetry. So I'll say later what I mean by enhanced supersymmetry and how much supersymmetry I actually need. The idea is that there's been some developments in the last 5 years or so in derived geometry, and I want to explain how certain partition functions and Hilbert spaces can be computed using those developments in derived geometry. So I'll give a more or less direct way to go from physics to some rigorous models for these. And as two main motivating examples, I want to talk about these two. So the first one is, if you look at 8-dimensional equals 1 super Mills, it admits a topological twist, so you can put it on a curved spacetime. And if you put it on a Calabi-Yau fourfold, it has enough supersymmetry to run this machine. And I will explain how to get or how to write down certain precise expression, which will be the partition function of this super Mills. And for the Hilbert space, here's another example. If you look at 7-dimensional super Mills, and again, it admits a topological twist, so you can put it on curved spacetimes. And I'm going to look at the spacetime of the form Calabi-Yau threefold, which is something 6-dimensional cross R. So let's say maybe Calabi-Yau threefold is X. So I'm looking at the spacetime X cross R. And so I can consider the Hilbert space on the spacetime. And again, there will be a model for this Hilbert space in the topological twist in terms of derived geometry. Well, the main problem when you're trying to do these calculations of partition functions is that, well, if you have theories with enough supersymmetry, you can apply supersymmetric localization to reduce to some fine-dimensional problem. But that fine-dimensional problem, you have to integrate over something singular. And so it's usually unclear how to make sense of that. And I will just explain how one can make sense of those kind of integrals using derived geometry. Okay, let me begin with a very basic example, which is going to be very important. So this is a zero-dimensional supersymmetric theory, meaning the space-time is just a point. So there's no space-time. And so really there's just the target space, which is what I call M. Okay, and to define this n equals 1, what I call n equals 1 sigma model, well, I have to choose, first of all, a manifold M, which is my target. On that manifold, there is a real vector bundle. So that's where the fermions will live. That vector bundle comes with symmetric bilinear form and a connection. And there's also a section of the vector bundle, alpha. Okay, so the fields are, so the bosonic fields are just given by maps into the target space. So here the source is just a point, so it's just an element of the target. And the two fermions are given by a vector field and a section of the vector bundle. So I'm not going to write the supersymmetry, but you can guess, yeah, you can imagine what it might be. So maybe let me just write two obvious ones. Delta phi is chi, delta chi is 0, and then delta psi has a slightly more complicated expression, but not too difficult. Okay, then you can write down the action functional for this toy model. So maybe some of you have seen this action functional. Okay, so I will maybe not comment on this action functional, but what I want to say is that if you want to write down the partition function, so I will just schematically write integral d phi, d chi, d psi, e to the s, maybe is. Well, to compute this partition function, you first integrate over psi. And what you discover is this formula for the partition function in terms of integral of some differential form. This differential form is exactly the Euler class that appears in the Matthias-Gaberdiel formalism. So if you integrate over, so I first integrate over the psi fields, then I reduce to some integral over phi and chi, which just combine into integral of differential forms over the manifold. Okay, so the upshot is that the answer is the integral of some explicit differential form, this differential form, this Matthias-Gaberdiel Euler class. Whatever it is, it has the same cohomology class as the usual Euler class. But the reason it's nice is that it localizes the Euler class to the zero section of alpha. Okay. And so one way, if you think now about this localization, one way to write down this partition function is just integral over the zero locus of of the section alpha of a certain fundamental class of X. Well, this makes sense if X is actually a smooth manifold, then this formula makes sense. But if X is not a smooth manifold, you have to do something. Okay, and then there are three main problems to make sense of this partition function. One of them is non-compactness of X. I will not say much about this problem. I will not be able to resolve it in any other way. The second one is you have to integrate over the fermions over psi. And for this, you need to choose an orientation on E. Otherwise, there's going to be an anomaly. Okay, and the final issue is the one I already mentioned, that to properly make sense of this, you want X to be a smooth manifold. So for instance, you can perturb alpha. so that the intersection of the graph of alpha and the zero section is transverse. Okay, and if the intersection is transverse, then this is just going, X is just going to be a collection of points, and then the partitioning function will be just the usual count. Okay, so this is a very classic story. And now if you have a higher dimensional supersymmetric theory and you consider it on a curved spacetime and you apply a topological twist, then hopefully you will have at least one supersymmetry. And so the compactified theory will be of this form, except M will be infinite dimensional and E will be also an infinite dimensional vector bundle. But the idea is that even though E and M are infinite dimensional, the zero locus might in some sense be finite dimensional. Okay, and so really we don't want to think of the partition function in this way because it's infinite dimensional. And really we want to think about the partition function as the integral of some fundamental class of the zero locus. So that's the supersymmetric localization. Okay, so this is the zero-dimensional example, and the one-dimensional example is very similar. So this is just supersymmetric quantum mechanics, like in Witten's paper. So in this case, I choose a Riemannian manifold, and I have a closed one form. So for instance, this one form might be exact. And then you can look at the Hilbert space in the topological twist. So it means I look at the cohomology of the Hilbert space with respect to the differential Q, where Q is my supercharge. And Witten explains that this Hilbert space should be thought of as Morse homology of H. More generally, if you actually have a closed one form, not an action not just the potential H, then you want to look at what's called Novikov homology. Okay, and again, if you're really interested in Hilbert spaces for higher dimensional supersymmetric theories, then what you do is you have a higher dimensional theory, you compactify it on codimension one submanifold, and you get supersymmetric quantum mechanics. But again, as before, there are problems. This manifold is usually infinite dimensional. And so really, you want to replace this manifold, this infinite dimensional manifold, by the critical locus of H. So in some sense, you want to reduce your calculation to something finite dimensional in terms of the critical locus of the potential, but the critical locus of the potential might be something very singular. Okay, again, there are two problems similar to how you've had these problems in zero dimensions. So if the manifold is not compact, which is usually the case in infinite dimensions, then the Morse differential will not necessarily square to zero. Okay, and the second example is, the second problem is that, well, if H is really not a Morse function, then it's not clear what you mean by Morse homology. So at least the critical locus should consist of isolated points. Okay. And I want to consider an example of how you get an example of this twisted Hilbert space. So let's consider a pure 4G n equals 2 super Mills with some gauge group G. So this is a pure theory. This theory has a topological twist, which is called the Donaldson twist. So this was considered in the original paper written on topological twists. So I can put it on curved spacetime, and I consider my spacetime to be some 3-manifold cross R. So now I can compactify this 4-dimensional theory on this manifold N, and I get just a supersymmetric mechanics on R. In this case, you have supersymmetric mechanics on R into the space of connections on the 3-manifold N, and H, this potential is going to be the Chern-Simons functional. Okay, and then if you look at the critical locus of the Chern-Simons functional, so the space of all connections is infinite dimensional, but the critical locus is fine dimensional. So this is the space of flat connections.
Do you hit an action with you have the Chern-Simons form? Do that explicitly? You hit explicit or is it just mathematical?
Sorry, could you say it again?
When you do this, do you get explicitly an action with the Chern-Simons term, or it's just a mathematical statement that you have to obtain this?
No, this is a precise calculation you can do. I forget at the moment who has done this, but it's been done in the early 90s, this kind of calculation. So you just write, n equals 2 supergain mills, apply the twist, and rewrite everything in terms of maps from R into something in terms of N. And you really get supersymmetric mechanics, and then you see the potential in the action. Or for instance, if you just unpack the supersymmetries, because the potential appears in the supersymmetries. Yeah, so in this case, H will be literally the Chern-Simons action function. Okay, so in this case, the critical locus will be the space of flat connections on N. And this is in some sense a finite dimensional object. It's not quite clear what you're supposed to do with this finite dimensional object in this case, but people have made sense of this twisted Hilbert space, namely Floer-defined instanton Floer homology of the 3-manifold N, which is supposed to be the Morse homology of the Chern-Simons function. Okay, so this is a fairly classical story, and this is what I would mean when you have a minimal amount of supersymmetry after the compactification. So what I want to talk about next is what happens when you have more supersymmetry. So things will simplify, first of all. And second, you will actually be able to write answers in terms of these fine dimensional models. Okay, so let me begin by explaining supersymmetry enhancement in 0 dimensions. Okay, so to define this n equals 1 sigma model, I said that I choose a real vector bundle with a bilinear form and a connection. Now let's assume that if you look at this vector bundle, you complexify it, so you get the script E, what I call, and you look at the 0-1 part of the connection, this is actually a holomorphic structure. So in other words, the 0-1 part of the connection defines a holomorphic structure. This vector bundle. Right, I forgot to say that actually M is also supposed to be complex manifold in this case. And the last thing is that I had this section of the real vector bundle E, And I want this section to actually be the real part of a holomorphic section of the complexified bundle. Okay, so you have this beta, which is a section of the complexified bundle. Its real part has to be the original section alpha. And also this new section, the holomorphic section, has to be isotropic. Beta beta, the pairing is 0. So in this case, you can write down 2 commuting supercharges. And some linear combination of those will give you the original n equals 1 supercharge. Okay. Now, in this case, you get n equals 2 supersymmetry. So one thing you get is extended. So once you have extended supersymmetry, you have R symmetry. In this case, the R symmetry group is SO2. And using this R symmetry, you can actually endow the space of fields with a grading. Because I'm talking about SO2, I actually need to complexify the space of fields. So I now consider the complexified space of fields. And instead of being a supermanifold, so instead of fields being just Z2 graded, R symmetry enhances the Z2 grading to a Z grading. And second, the second fact, which is might sound a little bit random at the moment, is just an observation that this complexified space of fields carries the symplectic structure. So if you write down the complexified space of fields, basically you'll see something that looks like essentially the cotangent bundle of M, and then there's going to be E in degree -1. So the cotangent bundle has a symplectic structure because I consider cotangent bundle where the cotangent fibers have certain natural degree. The symplectic structure will have a degree -2. And fermions were lived in this orthogonal vector bundle, which I put in an odd degree. So it's going to give me an even symplectic structure. Okay, so this is going to be a symplectic structure of degree -2. Okay, so that's the first fact. And the second fact, it's again, so far it looks like a random observation, is that actually you can go back. So if you have any -2 shifted symplectic manifold, so more precisely, this statement has been proven in the setting of algebraic geometry. So you consider -2 shifted symplectic derived scheme. Then there's a Darboux theorem for those. And the Darboux theorem says that locally, every -2 shifted symplectic manifold is of this form. So in other words, you have a smooth manifold M or smooth scheme M. You have a vector bundle E with an orthogonal structure. You have a section which is isotropic and so on. So exactly this structure. Well, and the natural question is, okay, you look at the space of fields, it has some symplectic structure. First of all, it's an even symplectic structure. So that's somewhat unusual because I'm just talking about something in 0 dimensions. If you think about the Bataille-Vilkovisky formalism, you would expect an all symplectic structure. So this is something different. Well, and then, yeah, natural question is it useful for anything? Can you use this shifted symplectic structure to say something about the theory? Well, the answer I want to explain is that actually, yes, this shifted symplectic structure is what will be used to give rigorous models. Okay. Any questions so far? All right. let me briefly mention an analogous picture in one dimension. So in one dimension, I had a Riemannian manifold to get n equals 2 supersymmetry. So this was n equals 1D n equals 2 supersymmetry. And now if you have not just Riemannian manifold, but a Kähler structure, and moreover, the potential H is a real part of some holomorphic function, let's call it W, then in this case, supersymmetry enhances from n equals 2 to n equals 4. So again, you can just write four supercharges, and then some linear combination of those will give rise to the original 2 supercharges. Okay, so the upshot is that what you have in this context is you have a Kähler manifold, or let's just think about complex manifold, M, and a holomorphic function, W. Again, as I said, the supersymmetric localization you want to do is to the critical locus of W. So you want to replace this data M and W, which is some infinite dimensional gadget, you want to replace it by the critical locus of W, which is something finite dimensional. Now, the critical locus of W can be enhanced to a derived object. So if you think about Batalin-Mikulowski formalism, this precisely gives you a derived object. This derived object has a symplectic structure, this derived critical locus. The symplectic structure has degree -1. So if you invert it, you get a Poisson bracket of degree +1, and that's the Batalin-Mikulowski anti-bracket. Okay, so maybe let me summarize what happened in the supersymmetry enhancement. In 0 dimensions, the complexified space of fields carried a -2 shifted symplectic structure, so symplectic structure of degree -2. And in this one-dimensional case, you get a -1 shifted symplectic structure. Okay, so next I want to explain what one can do with these and how this relates to the original physical problem. Before I do that, I want to explain from physics why the space of fields actually carries some kind of symplectic structure in 0 and 1 dimensions. Oh, the idea is the following. So let's look at this n equals 2 supersymmetry algebra in 0 dimensions. So that just means you have, so the supersymmetry algebra in this case is just the odd abelian Lie algebra of dimension 2. And so in this case, you have a family of supercharges. So this is the family of lines inside of C2. So you get CP1 family of supercharges. Okay, and then you can consider twists with respect to any of that supercharge in that family. Now, if you analyze this family will have a special point which is simpler than the others. At the special point, so for some special value, for some special supercharge, what you get is an analog of the BF theory in 0 dimensions. So what I mean by that is if you look at the space of BV fields or complexified BV fields, then you just get a -1 shifted cotangent bundle of something. Okay, so for instance, if you imagine that you have a theory with the zero action functional, then the space of BV fields will be like that. So this is a particular simple example of BV theory. Okay, so this is what happens at the special point. And then you can deform away from the special point by considering a family of twists. Now, if you deform the theory, well, that means that you need to deform this space, or in other words, you need to add a non-trivial action function on this. Okay, so an action functional on the space, well, it's going to be a function of degree 0 on the space. Okay, but function on the space is just a polar vector field on the base, on F. Okay, so what you get is a polar vector field on F, and then the classical master equation for this action functional. So you want the deformation to still be a BV theory. So the classical master equation tells you that this Poisson bracket, so this polar vector field, is actually integrable. So this polar vector field will actually be a Poisson bracket. And if you look at the shifts, it will be a degree 2 bivector. So it's going to be a -2 shifted Poisson structure. So degree of pi is, as a bivector, is 2. It's a -2 shifted symplectic structure. Okay. So basically, the upshot is that this is some kind of secondary structure to the usual BV structure in the presence of extended supersymmetry when you have this family of twists. You can also do this in 1 dimensions. So in 1 dimensions, you have n equals 4 supersymmetry. So that means the odd part is 4-dimensional, and the even part is 1-dimensional. If you look at the space of supercharges, so it's the space of lines in C4. So the space of lines in C4 is CP3, and then you want to look at square 0 supercharges. So that's going to be a quadric in CP3, so that's CP1 cross CP1. Okay, and then you can again repeat the similar stories. There's going to be a class of superchargers which are particularly simple, which give where, for instance, the classical phase space. So in this case, phase space will be simple. T star of something. Let's call it again complexified fields. And then deformations of that will be given by a function on the space satisfying classical master equation. So that's again going to give you a Poisson structure, but that Poisson structure has degree 1 because this is ordinary cotangent bundle. Okay. Let me again pause for questions because next I will switch gears and talk about derived geometry a little bit.
Can I ask maybe a naive question, Pavel?
Yeah.
Is there just one special point here? Because normally I could imagine, for example, that there's like a C star action, but then there would be 2 fixed points of that C star action on this P1.
Yeah, that's a good question. I think indeed that there are 2 special points. The 2 special points correspond to basically, they give you essentially the same space, except one of them has complex structure with a minus sign. Yeah. So it corresponds to two choices of the complex structure, J and minus J.
Okay, perfect. And so those are both of BF type, and then in between you get something.
Exactly. Yeah, so you could deform maybe you can imagine that at the other pole you also have kind of anti-holomorphic BF, and then you can deform from the other side as well. Good question. All right, so let me talk about derived geometry now. Okay, so what did I want to do? So I had this vector bundle, so that E was a real orthogonal vector bundle. There was a connection and so on. And there was a section alpha. And then I want to apply some kind of supersymmetric localization to reduce this integral of the Euler class of E. I want to reduce that to just the integral over the zero section. And of course, the main problem is that this intersection of alpha with the zero section might not be a smooth manifold. So the intersection is not transverse. What I said is that in the case that I'm talking about, when I have extended supersymmetry, actually, so this was this complexified space of fields before. I have a -2 shifted symplectic structure on the space of fields. And then given any -2 shifted symplectic structure, -2 shifted symplectic scheme, there was a sequence of works defining the notion of virtual fundamental class in this context. This virtual fundamental class, this is something for a, so this is a complex symplectic scheme. And the way they do this, at least Boris of Joyce do that, is they extract a real vector bundle with a real section. So essentially the way they define this virtual fundamental class is precisely using a real model like this. Okay, so it's some class in homology of X. The degree of the homology class is the virtual dimension of X. And this homology, well, I said it's the Borel-Moore homology, so locally finite chains. And then, for instance, if X is compact, then you can integrate this virtual fundamental class, and you can get a number. So the upshot is that whenever you have extended supersymmetry in 0 dimensions, then equals 2 supersymmetry. So you start with some higher dimensional field theory, compactify it down to 0 dimensions, and suppose your space-time is such that you have extended supersymmetry. Then you get a sigma model of the type I mentioned. And then on complexified space of fields, you get a -2 shifted symplectic structure. And then you can define the partition function to be just the integral of the virtual fundamental class of Boris of Joyce, Freedom, and O. Helms. Okay, and the idea is that in all the examples of twists of at least supersymmetric gauge theories, so twists, so whenever you actually have this extended supersymmetry, this complexified space of fields is actually a finite dimensional -2 shifted symplectic. It happens to be stack, but that's maybe irrelevant for the talk. The key word here is finite dimensional. So in fact, after supersymmetric localization, you can actually make this definition, and this is something that's properly defined. Okay, and again, let me just repeat the original idea is that one way to make sense of this virtual fundamental class is to perturb the section so that the intersection of the section with the zero section is transverse. And here, instead of perturbing the section, you just remember the derived structure. And then you can still define this virtual fundamental class. Okay. So this is the story of how you define a partition function in 0 dimensions. And I want to just mention a similar story in 1 dimension. Okay, and again, so we want to talk about somehow Morse homology for a function which is not Morse. In our case, M is some complex manifold, and W is a holomorphic function. And then the potential is the real part of this holomorphic function. As I said, I want to reduce from this data of M and W, which is where M is usually something infinite dimensional, like the space of all connections, to the finite dimensional model, which is the critical locus. And now the critical locus has a shiftless symplectic structure. Finite dimensional -1 shifted. Symplectic scheme. Okay. Now, just purely in derived geometry, Joyce with collaborators, they've defined a certain perverse sheaf. So it's a complex of sheaves for any -1 shifted symplectic scheme. And the idea of this complex is that whatever Morse homology might be in this holomorphic context, when H is the real part of a holomorphic function, it's going to localize as a sheaf on the critical locus. So in other words, there are no instant corrections. There's nothing connecting different critical points in this context. So in the paper, with Brian, we give more motivation for this proposal. So why that's the right Hilbert space by connecting this to BV quantization. But let me not say that unless there are questions. And so the upshot is that, again, in this case, you look at the critical locus. The critical locus of W will have this -1 shifted symplectic structure. So you can define the cohomology of this perverse sheaf, and that's the answer for the twisted Hilbert space in the supersymmetric mechanics. And in this case, you could, again, if you just try to make sense of Morse homology, to define Morse homology, you have to fix the issues of compactness, because then if the space is non-compact, the differential might not square to 0, and then transversality. So if the function is not Morse, then the Morse complex is just not defined. But in this case, it's just it always makes sense if X is actually finite dimensional. All right. So I want to end with some examples. So let me begin with some examples of twisted Hilbert space you get from this construction. I want to explain that those twisted Hilbert spaces actually relate to something that's that was known in math literature. Okay. So the first example is, let's look at maximally supersymmetric Yang-Mills in 4 dimensions. So there are many topological twists, and I'm going to consider what's called the Vafa-Witten twist. And that's the same, for the purpose of the Hilbert space, that's the same as the twist considered by Marcus or Kapustin-Witten. Okay, and then you can compactify it on a 3 manifold to get the supersymmetric mechanics. So the story is very similar to the case of the insular floor homology that I started with, where you instead of looking at n equals 4, you look at n equals 2 supersymmetric Yang-Mills. In that case, you get supersymmetric quantum mechanics into the space of G connections, and the potential was given by the Chern-Simons functional. Now, instead of G connections, you look at complexified connections, and the potential is the complexified Chern-Simons function. So this is the calculation we do in the paper. And then, then you can compute the critical locus of this complexified Chern-Simons functional, and that's the space of flat GC connections. This space is a very nice fine dimensional -1 shifted symplectic scheme, or stack in this case. And so you can define you can define a twisted Hilbert space via the proposal I mentioned on the previous slide. So it's the cohomology of this perverse sheaf on the critical locus, which is the space of flat connections. This cohomology was considered in the math literature. It was defined maybe about 3 years ago by Abuzit and Manolescu. They call it complexified instant floor homology. So the idea is that it's precisely the complexification of the n equals 2 story where you get the usual instant floor homology. Okay. So another example is if you look at something in 7 dimensions. So if you look at 7-dimensional super Yang-Mills, you can compactify it on Calabi-Yau threefold, and again you will have extended supersymmetry. In this case, the story is very similar to the first example, except you replace the usual Chern-Simons functional by the holomorphic Chern-Simons functional. So W will be holomorphic Chern-Simons functional. And then again, you can formulate the Hilbert space as the cohomology of this perverse sheaf on the modular space of holomorphic bundles. This cohomology of this perverse sheaf is exactly what is known as categorified Donaldson-Thomas invariant. So this was again defined by in 2012 by Kim Lee and Joyce with collaborators. Okay, so the final thing I want to mention is one example of a partition function, again using derived geometry. So let's consider 8-dimensional super Yang-Mills. Again, you can consider a topological twist of that, and you can put it in Calabi-Yau fourfold. If you compactify it in Calabi-Yau fourfold, in 0 dimensions, you will have n equals 2 supersymmetry. In this case, this complexified space of fields, you can compute that, and that's going to be, again, the moduli of holomorphic bundles. This is moduli space of holomorphic bundles. On this Calabi-Yau fourfold. And this is again a nice -2 shifted. symplectic stack. And then if you restrict to maybe stable bundles, so that you actually get a scheme, then you can define the partition function by computing integral of the virtual fundamental class. And this is what was defined by Cao and Leung, which is called the DT4 theory. So it's the Donaldson-Thomas theory for Calabi-Yau fourfolds. They defined it using differential geometry, and then this work of Boris of Joyce and the others was an attempt to define it using derived geometry. Okay, but the upshot is that this Donaldson-Thomas invariant for Calabi-Yau fourfolds is exactly the partition function of a-dimensional spring emnils. Okay, so I'll stop here. Thanks.
Well, thank you very much. Any questions?
There's a question in the Zoom. Go ahead.
Thank you. I have a question about the potential. In the -1 shifted case, as you explained, there's the local structure, local Darboux theorem that gives the structure of the manifold as critical locus, and then there is this perverse sheaf of vanisher cycles that is so important. In the -2 case, the situation is slightly different. There is a globally defined potential, but it's not a function. It is a section of a real bundle, the dual bundle to the one. So my question is, given this global potential in the -2 shifted case, is there any kind of role for it, the way that this W in your case that you were describing plays in the case of -1 shifted structure?
I'm not sure. I haven't thought about that. That's a good question. I don't know. Sorry.
I maybe have a naive question, but the so these are at the end. This is an integer, right?
In the case of a maybe it's something maybe a rational number.
I thought if it's a DT invariant, if you have a scheme, then it's an integer, and if it's a stack, you have a rational number. But
I think it's currently it's something like you have to join 1/2. I'm not sure. I don't think the fundamental class is in the integer homology. At least in the O-Thomas approach, they have to divide by 2 somewhere.
My question is whether there's a way to see this from your formalism, or whether this is something you only know because you can compare it with other definitions.
No, I wouldn't say it falls. At least it's unclear from what I said. Of course, the idea is that you should be able to perturb this section and get a transverse intersection, and then you would just count. You would get a signed count of points. That would be an integer. Yeah, but I don't know.
If there are no other questions in the Zoom, then let us thank Pavel again for his talk. Thank you very much for visiting. Stick around for the next talk, of course. We are switching now. Do we need a break in this? There's a 10-minute switch, right? But I think we just do the switch.
Next speaker is Matthias, right?
Matthias.
Can you hear me already?
Yes, yes, I'm trying to set up my my iPad. Can you see this?
We can see you, we can see the slides, so it's good to go. Right, so next speaker is Matthias Gaberdiel, and he will tell us about the string dual of 3 n equals 4 super mills.
Okay, well, thank you very much for the introduction and invitation. I would have loved to come to Heidelberg, but unfortunately I couldn't get away from Zurich, so it has to be remote. Okay, so my talk is somewhat has a different style than many of the other talks. So I'll try to motivate it in a way that maybe also people from a little bit further afield can understand what we are up to. So this is about the ADS-CFT duality, and I think what you need to know about it is that this is an important problem in string theory to understand really how it arises. It is very influential because it relates two rather different theories to one another, namely some superstring theory on an ADS background to a gauge theory living on the boundary, and this has been extremely influential over the last 25 years or so. Now, there is very much evidence that this duality is correct, that it captures interesting dynamics, that it's not just kinematical, that there are plenty of consistency checks that have been performed. But I think we are still short of a real proof. And I also think this is more than some sort of aesthetic or nice to have situation. We would like to apply this duality in situations that are not directly ADS 5 process 5, say. And in order to do so, we have to have a better understanding of what really makes this duality work, how general it is, what pieces are crucial, what pieces are accidental, and so on. And I think unless we understand the duality, at least in one example, in great detail, we will not be able to understand what exactly makes it tick. So what our aim has been for the last essentially 10 years, and so this is largely based on work with Rajesh Goprakuma, involving also some other people, as I mentioned as I go along. So our aim is to try to derive the ADS-CFT duality in at least one simple setting, to understand how it works there, and then maybe understand more general lessons from it. So sometimes we hear people say that the ADS-CFT correspondence is a strong weak duality, and this comes from the fact about how the parameters of the string theory side of the picture and the gauge theory side are related to one another. And very roughly, I mean, but this is sort of the essential piece that you have to take away from it. There are really two independent parameters that characterize the two theories, and they are related in a very specific manner in the context of this ADS-CFT correspondence. So there's the rank of the gauge group, which is n, and the rank is inversely proportional to the string coupling constant. And we should always look at the situation where n is large, so that the string coupling constant is small. The string coupling constant is the measure. It's the coupling constant that tells you the probability for a string to split, for higher genus contributions relative to the lowest order contributions from a string worldsheet perspective. So that side is fine. I mean, we want to be at large n. The gauge theory simplifies at large n, and we want to be at small g string. So that's a no-brainer what we should do there. The other, I mean, it's really a two-parameter space. We have really two parameters. One is the string coupling constant, and one is the radius of the ADS space, or the inverse cosmological constant, in terms of the typical size of a string, what is normally called the string length, or LS here. Now, this quantity, according to this dictionary, is proportional to what's called the Tuft parameter. The Tuft parameter is a certain combination of the coupling constant and the rank of Superang-Mills, and it is the effective coupling constant of the gauge theory in the large n limit. So if I take n large, then the Tuft parameter characterizes the effective coupling constant of the gauge theory, And what this dictionary tells you is that this coupling constant is to be identified with some power of the radius in terms of string units. So this is where people normally, this is the reason why people normally say ADS-CFT is a strong weak duality, because you see, if you take the TUF parameter small, then that means the radius is of the same order of the string length, i.e. the system is extremely stringy, and that's a regime that's not that easy to access from the ADS side. From the ADS side, it's easy to access the regime where the radius is much bigger than the string length. That's the regime in which you can describe it in terms of supergravity. So that's the regime where this is sort of perturbative, but then then this corresponds to the coupling constant in the gauge theory to be large. So one side is always under good control and the other side is under poor control, and that's what people usually refer to when they say it's a strong weak duality. Inherently, it's very difficult to prove because typically you have one side under control and not the other, but not both sides at the same time. So this is the basic problem why people haven't proven the ADS-CFT duality many years ago. It's not so obvious how you're going to do it. Now, if you think about it, on the gauge theory side, we have very little choice. I mean, on the gauge theory side, we are very far away from understanding strongly coupled gauge theory. So we are de facto forced to choose lambda to be small. So when you do that, what this means is that the radius in terms of string units is small. And another way of saying this is that the size of the string is relatively large, or rather the string has the same size as the space in which it propagates. So this is usually referred to as tensionless strings. And this is the regime of string theory that corresponds to the situation where the TUF parameter is small, i.e. to the weakly coupled gauge theory regime. And this is an old idea. This was observed many years ago, that this is a regime where also something miraculous should happen on the string theory side, but you are very far away from the regime that people usually study, i.e. you can't describe the background in terms of supergravity. Now, what would you expect to happen on the string side when you look at this weakly coupled Super-Yang-Mills theory? You should expect, you see, weakly coupled Super-Yang-Mills theory is a free theory, or essentially free theory, so it has lots of symmetries, and somehow they should be reflected on the string theory side. And the idea is that while you can't describe it in terms of supergravity, there should be some other redeeming feature that allow you to make sense of string theory in such a background. And the basic idea or the basic tenet behind what we have been trying to do is that because this is so symmetric, it has this higher spin symmetry and so on, you may hope that while the supergravity description will be extraordinarily complicated, maybe it will have a simple worldsheet description. So as you probably know, the fundamentally correct way of describing string theory is in terms of the worldsheet of the string maps from the worldsheet into the target space. And what you could hope is that the weakly coupled Super-Yang-Mills regime corresponds to a string theory that is very complicated because it's highly curved, but maybe it has a simple, a solvable, maybe even a free worldsheet description. So this is sort of our working hypothesis. This is our idea that that's maybe is the regime where we have a chance to prove ADS-CFT. And what we should be looking for is what can we say about the honest string description in this tensionless regime, and can we make sense of this worldsheet description concretely? Now, this is sort of, I mean, it's very general so far. So you can ask yourself, I mean, is there any evidence that this seems to work? And in fact, there is, we feel there is relatively good evidence for this to work, at least in the case for ADS3. So ADS3 is the three-dimensional anti-de Sitter space, and the background string theorists like to look at is the three-dimensional anti-de Sitter space times a three-sphere times a four torus. That makes up the 10 dimensions of critical superstring theory. And originally part of the original Maldacena proposal was that this should be dual to a certain two-dimensional conformal field theory, namely to the symmetric orbifold of T4, which is nothing else that you take n copies of T4, and then you divide by the symmetric group, which commutes the n copies. So this is some sort of on the same level as ADS5 × S5 and n equals to 4 Super-Yang-Mills. This is sort of a part of the string folklore that these two descriptions are dual to one another. Now, obviously, one has to be a little bit careful because there's a whole moduli space of these conformal field theories. And the symmetric orbifold theory is one specific point in this moduli space. But what one may believe is that this symmetric orbifold point is really the analog of free super Yang-Mills. I mean, you see, it's the 4 torus, which is basically 4 bosons, 4 free bosons and 4 free fermions. You take n of them, so you have 4n free bosons and 4n free fermions. And then you just divide by some global group, which is like the sort of gauge invariance of super Yang-Mills. So you could believe that the symmetric orbifold theory is really the lower dimensional analog of free super Yang-Mills. So you would believe that this is the analog of the 't Hooft parameter being small. So you could ask, can we identify the dual worldsheet theory? And can we see that there is something very special happening for this worldsheet theory? Now, what we propose and what by now we have very good evidence for, and I'll review some of this evidence, is that in this limit, that the corresponding string theory is the background ADS3 crosses 3 at the tensionless point where it is very, very small. And I'll explain in more detail what I mean by this level here. But in fact, in terms of this so-called hybrid formalism of Berkowitz, Waff, Witter, it means that you have to take the super Lie algebra PSU1,1/2 at level 1. And the super Lie algebra arises because that describes the geometry, the symmetries of ADS3 crosses 3. So in any way, what we propose is that a symmetric orbifold theory is exactly dual to a very specific string worldsheet theory. The string worldsheet theory consists of 4 symplectic bosons and 4 free fermions, which furnish a free field realization of the super Lie algebra, super affine Lie algebra PSU1,1/2 at level 1. And what we've shown, and I'll review this a little bit later, is that if you apply the usual string procedure to this worldsheet theory, you reproduce exactly the degrees of freedom of the dual symmetric orbifold, and you also recover the structure of the correlation functions. So this is an example where we've gone very, very far towards actually proving the ADS-CFT correspondence. We've written down a specific worldsheet theory. We can analyze it because it's a solvable worldsheet theory. We can determine the physical spectrum, and it matches exactly, not just on the BPS level, the entire spectrum reproduces exactly the single particle spectrum of the symmetric orbifold of T4. And furthermore, the structure of the correlation functions are also correctly reproduced. Now, this is what the first half of my talk will be about, to try to review for you how this comes about and the sort of structure that we see. Now, what we've been thinking about during the last few months, in particular this year, is whether we can sort of boost this up to actually find the worldsheet description for free n equals to 4 super Yang-Mills in 4 dimensions, i.e. going back to the sort of higher dimensional case. And again, that should be a tensionless string theory. And what we propose is that you basically just double the degrees of freedom from the ADS3 theory. So instead of having 4 symplectic bosons and 4 free fermions, we propose that the worldsheet theory consists of 8 symplectic bosons and 8 free fermions. And this, as it's not difficult to see, furnishes a free field realization of the pseudo-Lie algebra PSU 2,2/4 at level 1. And as a consequence, at least the global symmetries of n equals to 4 super Yang-Mills come out correctly. It's also similar to other ideas, in particular this twistor string of Berkowitz. And I'll try to motivate our proposal and then explain to you to which extent we've managed to see that this really reproduces at least the correct spectrum of free n equals to 4 super Yang-Mills. So there are still many gaps in our argument. This is at a much earlier stage in the development, but we feel this looks very promising, and it has all the right ingredients to describe the worldsheet description that's exactly dual to free n equals to 4 super Yang-Mills in 4 dimensions. And therefore, it really opens the door towards having a serious go at proving the ADS-CFT correspondence in that context, because both theories are under quantitative and detailed control. So we should be able to really check this in great detail and derive the duality, and hopefully that will teach us more general lessons about ADS-CFT. So this is sort of what I want to explain to you. So what I want to spend about half of the talk is to, or probably even a little bit more than half of the talk, to review how ADS3 works Then I want to explain to you why this motivates this generalization to ADS5 and what we can say about ADS5. And then I'll end with some conclusions and outlook for where we hope to go in the future. If you have any questions, please feel free to interrupt. So let me start by trying to explain to you in a little bit more detail how this ADS3 story really works. So the ADS3, the string theory in ADS3 cross S3, you can describe in terms of what's called the Maldacena-Oghori-Wessel-Minowitton model, and that is a fine description of it. But there's an alternative description that was invented by Berkowitz, Waffer, and Witten, primarily with the aim of switching also on Ramond-Ramond flux. But if you don't do this, if you just look at the pure Neveu-Schwarz background, then their description is basically like the Green-Schwarz version of the NSR version a la Maldacena-Oghori. And the key feature of it is a super Wessel-Minowitton model based on PSU 1,1/2. That describes ADS3 cross S3. And then you have a topologically twisted sigma model on T4, i.e. you just have 4 free bosons and 4 topologically twisted fermions. And then you have a cohomology that describes for you what the physical states of this worldsheet theory should be. And I mean, they derived it by starting with Maldacena-Oghori and doing some sort of field definitions, but you can also check that the spectrum agrees, and that has, I think people believe that this is exactly the same description. Now, what we are interested in is this theory at level 1, because you see the level of this is basically the size of the ADS3 cross S3 space. So K being large would correspond to ADS3 being and S3 being big in string units, and K small means ADS3 and S3 are small in string units. And remember, we are trying to find the analog of the tensionless string. So this should mean the regime where this is very small. So you want to take this at the smallest possible value that makes any sense. And the smallest possible value is K equals to 1. So we want to study the PSU 1,1/2 Wessel-Minowitton model at level 1. Now, as people know, level 1 theories, say for SU2 or SUM, they're very special, right? They're quite different from the Wessel-Minowitton model corresponding to SU2 at level K. They contain far fewer degrees of freedom. And as is famously known, SU2 at level 1 is really equivalent to a single circle. So the structure of it changes dramatically. So one may hope that also for this super Lie algebra, something special may happen at level 1. Now, the first indication that something special may happen is if you look at the bosonic subalgebra of the super affine algebra. So the bosonic subalgebra is just SL2. So SL2 is basically the same as SU1,1. So whether you call it, so this is really the bosonic algebra is SU1,1 and SU2, but SU1,1 I call SL2R, but this is really meant to be the same thing. And then the SU2 factor is the SU2 factor. And the way this bosonic subalgebra sit inside this super affine algebra is that the levels are the same. So in particular, you end up with SU2 at level 1. But as I just mentioned to you, SU2 at level 1 is quite a special theory. In particular, it only has 2 highest rate representations. I mean, as people probably know, SU2 at level K, the spin of the highest rate space can go up to K over 2. So the spin can be 0 or half for the case at level 1. And if you translate this into a dimension, it can either be the singlet or it can be the doublet with respect to SU2. So that's purely if you look at the SU2 part. But think about it, PSU 1,1/2 is a super Lie algebra. It has fermionic generators. And therefore, the highest rate states of a highest rate representation will sit in some sort of Clifford algebra coming from the fermionic zero modes. And you can organize the different terms in this Clifford algebra in terms of representations of SL2R and representations of SU2, which is what I've done here. So here, the first entry always describes the representation of SL2R. And I'm looking at the so-called continuous representation. So the spin is parameterized as a half plus IS. And alpha, this parameter alpha, labels for you the eigenvalue of the Cartan generator of SL2R mod integer. These are the 2 parameters that characterize the SL2 representations. And the second entry here is just the dimension of the SU2 representation. Now, this is the generic representation of these fermionic zero modes. And if you stare at them, then you observe that, you see, if you start here with n, there is a term here that will involve n plus 2. But on the other hand, remember for SU2 at level 1, the only allowed representations are n equals to 1 and n equals to 2. So even if I start with n equals to 1 here, I would get a representation that's not allowed here. So therefore, at level 1, the only representations that are compatible with the structure of this vertex operator algebra are the short representations. They must be shorter than the generic representations because the SU2 representations can't support highest rate representations where the spin is bigger than a half. So you can analyze this, and what you find is that apart from obviously the vacuum representation, the only allowed representations are these extremely short representations that consist of 3 summands. So this is basically a piece of that, but you basically just keep these 3, and all the other ones are set to 0. They must be 0, otherwise it's not a representation. So you have a strong shortening condition. And then if you study it, you find that this shortening is only possible if the spin that enters here in terms of these SL2R representations is actually equal to a half. You can't take any other value of the spin. So this representation theory, which to start with looks very, very floppy, seems to contain all sorts of stuff. At level 1, there's really essentially only one representation. But you have one free parameter, which is this alpha parameter. But apart from this alpha parameter, everything is fixed. And that's the only non-trivial highest rate representation apart from the vacuum representation. In particular, there's no continuum. And for people who sort of know the background of this a little bit, the continuum of this Wesselmino-Witten model was always deemed to be the reason why it can't be due to the symmetric orbifold. But at level 1, the representation theory is much more rigid. The continuum isn't there, and there is a chance that it matches with the symmetric orbifold. And as I'm about to explain to you, it in fact matches exactly with the symmetric orbifold. Okay, so this is the representation theory of PSU 1,1/2 at level 1. There are other ways of deriving it. In fact, there's a very useful way to think about PSU 1,1/2 at level 1, which is the fact that it has a free field realization. I mean, this is the way you should think about it, is that this is really the super algebra version of SU2. So SU2 at level 1 has a free field realization, say, in terms of a complex fermion modulo U1 or a single real boson. And likewise, the PSU 1,1/2 has a free field realization in terms of free fermions and what you may want to call symplectic bosons. So to be a bit more specific, the algebra that has a free field realization is U 1,1/2 at level 1. And it can be written in terms of these fields. So these are the standard fermions. They just satisfy usual anti-commutation relations. And then you have what are called symplectic bosons. So they the structure of the right-hand side looks like 4 fermions. So they seem to be spin a half, but they satisfy commutation relations rather than anti-commutation relations. So that's what that's what often called a symplectic boson. So they behave like a ghost. But these are the fields that generate, if you look at the suitable bilinears of them, they'll generate for you U 1,1/2 at level 1. And then in order to get PSU, you have to sort of gauge by some diagonal U1. And the diagonal U1 has basically this form. You basically couple the 2 symplectic bosons together and the 2 fermions together, and you sum over everything. And that's the thing you have to set to 0 in order to go from U 1,1/2 to PSU 1,1/2. So that's another way of describing this worldsheet theory. So in particular, we should be able to recover the structure of the representations from this free field description. And that is as straightforward as it goes. You see, these fields have basically a Ramond sector and a Navier-Schwarz sector. You have to choose all of them to be either in the Ramond sector or in the Navier-Schwarz sector. All of them should be half integer moded, or all of them should be integer moded. Because you see, the bilinears always have to be integer moded, so you have to choose the mode number once and for all. If you take them all to be half integer moded, then you just describe the vacuum representation of PSU 1,1/2 at level 1. And if you describe them all to be integer moded, you describe this short representation that I talked about before. So these are the only highest rate representations that this super Lie algebra has. So they will therefore appear in our spectrum of our worldsheet theory. So here's a sketch of what this looks like. You see, the symplectic bosons, they don't satisfy an anti-commutation relation. They satisfy a commutation relation. So you can go infinitely many times in either way, in this way. So unlike the fermions, this will not be a finite dimensional representation. It'll be an infinite dimensional representation. You can apply psi plus as many times as you like, and eta minus and so on, and you just walk to the right or to the left as many steps as you want. And then you have some choice exactly of how the offset is, and this choice of the offset translates into this alpha parameter that I was referring to earlier. So this is basically just reproducing this representation theory that I described for you before, more concretely from this free field perspective. Okay, so these are the highest weight representations, and this goes back already to the papers of Maldacena-Oguri. String theory in ADS3 process 3 doesn't just consist of these highest weight representations. What you have to do is you have to, in addition to these standard highest weight representations, you have to add in what are called spectrally flowed representations. So these are representations that you obtain from these highest weight representations by applying a certain outer automorphism of the PSU 1,1/2 algebra. So what's the outer automorphism? Well, it's most easily described in terms of the free fields. So I can define tilde modes and untilde modes that are related to one another in this fashion. And they clearly describe an automorphism because you see the commutators, they only care about that the sum of them has to be equal to 0. So as long as I shift one up and the other one down, the commutators will go into the commutator. So these are is an automorphism of this free field algebra. And then if you translate this into the generators of the PSU 1,1/2, you see that the Cartan generator transforms as such, and the Virasoro generator transforms as such. And I'm here only spectrally flowing the bosons. You can also spectrally flow the fermions, but whether you do or not is really a matter of choice. Now, when you do this, you see what happens is that the L0 eigen, so what you do is you take the standard Ramon sector representations, you regard it as a representation of the tilde modes. So the tilde modes act on this space like it's written, but then you interpret it as evaluated with respect to the untilde modes. So in particular, you can ask yourself, what's the L0 eigenvalue on this space? The L0 eigenvalue is what the L0 eigenvalue used to be minus W times what the J30 eigenvalue used to be. But because this representation is infinite in both directions, you see the J30 eigenvalue can go as positive as it wants for a given L0 tilde eigenvalue. If you go further to the right here, then L0 will get more and more negative. So these spectrally flowed representations are not conventional highest rate representations. They're really inequivalent representations relative to the familiar category of highest rate representations of the super affine Kac-Moody algebra and the super affine algebra, and the observation of Maldacena-Oguri, and that's also reasonably well motivated from string theory, is that you need these representations on your worldsheet description in order to describe string theory on ADS3 crosses 3. I mean, the reason is basically, you see, when you describe string theory in Minkowski space, the L0 spectrum on the worldsheet is also unbounded because you need to have sufficiently, I mean, you want to have arbitrarily many excitations, but still satisfy the Maxwell condition. So your L0 spectrum, before you impose the physical state condition, must be unbounded. And the same is true here. This is basically why you need these spectrally flowed representations, so that you get an unbounded L0 spectrum, so that the resulting physical spectrum has a chance to look like anything like a string. Anyway, that's the old proposal of Maldacena-Oguri, that you take the representations, the highest rate representations, and you add in the spectrally flowed images, and that describes your full worldsheet theory. And we are simply doing exactly the same thing here. In our case, we are taking, in fact, just a Ramon sector representation. The Neveu-Schwarz sector is sort of measure 0 and doesn't appear. And we add in all the spectrally flowed images, and that describes our worldsheet theory. That describes the Hilbert space of the, well, not Hilbert space, it's a non-unitary theory, so that describes the vector space of your worldsheet theory describing string propagation on ADS3 crosses 3. Now, since this PSU 1,1/2 theory has this free field realization, or because it has many null vectors, whichever way you want to look at it, it has far fewer descendants than you would naively expect. In particular, you see, from the point of view of the free fields, you have 4 symplectic bosons to start with, but you have to divide out by this U1 constraint, and that effectively eats you 2 bosons. So you only 2 bosonic degrees of freedom left after you've gone to PSU starting from U 1,1/2. On the other hand, as many of you are familiar with, whenever you look at the string spectrum, you're basically have to impose the physical state condition, and the physical state condition typically eats 2 transverse degrees of freedom. So this naive counting suggests that after you've imposed the physical state condition, there are no transverse degrees of freedom left from the ADS3 cross S3 factor. And therefore, you would expect that all the degrees of freedom will come from the remaining T4 factor. Because remember, it's ADS3 cross S3 cross T4. The PSU bit only describes ADS3 cross S3. So what this argument tells you is that in the physical string, there won't be any excitations on ADS3 plus S3. All the excitations will come from the T4. And if you go through the systematics of it, what you find is that you reproduce exactly the single particle spectrum of the symmetric orbifold of T4. So you take this worldsheet theory, you apply the standard rules of string theory, you look at the physical states, you can enumerate them because it's a free field theory. And what you find is that it matches exactly the single particle states of the symmetric orbifold of T4, i.e. it reproduces exactly what we thought should be the dual CFT. And the way the dictionary works is that the W-cycle twisted sector of the symmetric orbifold, I'm not going to go into detail what that is, but that's a specific piece of the symmetric orbifold theory that comes exactly from the sector with W units of spectral flow, i.e. from the sector where you have done this for W being the corresponding number, the corresponding integer. So this is quite striking already because that gives you, reproduces exactly the spectrum of this dual CFT from the worldsheet, and not just for the states that are protected by supersymmetry, it reproduces the entire set of physical degrees of freedom. Now, furthermore, you can ask yourself, how about the correlation functions? I mean, whenever you want to show that two things are the same, two theories are the same, you typically want to show that the spectrum agrees, and then you want to show that the correlation functions agree. So what can we say about the correlation functions? Now, the correlation functions of the symmetric orbifold theory have quite a remarkable structure. So suppose you're looking at a symmetric orbifold theory and you're evaluating it on a sphere, that is the boundary of ADS3 is a cylinder. So if you compactify it, you get a sphere. So you're going to calculate these correlation functions on the sphere. There's a smart way of calculating these correlation functions by going to the so-called covering map, by looking at some surface that covers the space where your symmetric orbifold vertex operators are inserted, and you're looking for a holomorphic map from some Riemann surface down to the sphere so that near each of the insertion points up there, you get mapped to a point down here. So xi gets mapped to zi gets mapped to xi, but near z equal to zi, there's a critical point in the sense that it maps it to zi gets mapped to xi, but in the neighborhood, you cover it wi times. So this is a statement about how symmetric orbifold correlators can be calculated, and that goes back a long time. On the other hand, it's quite natural, if you look at the 1/n behavior of these correlators, it's quite natural to believe that this covering surface should be identified with the worldsheet of the putative string theory, because then the way the genus appears in this correlation function calculation for the symmetric orbifold captures exactly how the genus expansion of string theory should appear, given that the G-string coupling constant is related as 1/n, as I mentioned earlier. So what it suggests is that maybe the worldsheet theory should play the role of the covering surface, but that should mean that if you calculate the worldsheet correlation functions in this funny theory, what you may hope for is that they localize exactly to those configurations where such a holomorphic covering map exists. So the statement that was proposed some time ago by Pachman, Rastelli, and Razamat, and that we've now managed to establish from first principles, is that if you look at this PSU 1,1/2 theory, you calculate the correlators of this vertex operator corresponding to spectrally flowed sectors, then these correlation functions are mostly zero. I mean, they're generically zero, and they're only non-zero provided that the ZIs, which are the points where you insert them on the worldsheet, conspire in such a way that you have a holomorphic map from the worldsheet to the space in which the dual CFT lives, such that Zi gets mapped to xi, and near Zi, the function has this form. This is a highly constraining property, and in fact, the set of covering maps is discrete. That's described by Hurwitz's theory. So there's a nice story about how this comes. But quite remarkably, what we find is that these correlators calculated in this PSU 1,1/2 Western Minority model at level 1 have this very remarkable property that they are essentially always 0 except when a covering map exists. And they take exactly this form. And you see, once they take this form, then when you do the integral over the worldsheet moduli, as you have to do in string theory you have to integrate over the insertion points on the string moduli, as well as the parameter that describe for you the shape of the torus and so on. If you do this integral, then there are exactly enough delta functions to turn this integral into a finite sum over the covering maps, and you reproduce essentially manifestly the answer that you can calculate directly from the symmetric orbifold. So this picture really quite suggestively reproduces all the structures that you know from the symmetric orbifold from what is essentially a free worldsheet theory, and a worldsheet theory that you can really construct and calculate, and for which you can establish statements like that, where you can really calculate these correlation functions and show that they have this property. In fact, the most elegant way of showing this property is not directly in terms of PSU 1,1/2, but again in terms of these free fields. And what we found is that these correlators satisfy this remarkable property that this combination of the symplectic bosons vanishes inside any physical correlator, where here you write down the covering map that maps the z's to the x's. So, and what you can show is that the covering map exists. That what it basically tells you is that the covering map is minus xi minus over xi plus. So you can express the covering map in terms of the symplectic bosons. And if the covering map doesn't exist, then the individual correlators have to be 0. And you can furthermore show that it's really a delta function localization. So this is the status of ADS3. And in that case, we've really matched the spectrum and the correlation functions essentially from first principles. And we have a very good and detailed understanding of how this duality works. Now this relation, if you know a little bit of twistor theory, this relation looks a little bit like the incidence relation in twistor space. I mean, this is to be identified with the coordinates of the space-time theory. So this really looks like two twistor fields being related by the coordinates. That looks like the way you go from the twistor space to the physical space. So this suggests that maybe the right way to think about this theory is that these free fields are really living in the twistor space of our space-time theory, rather than just being randomly chosen free fields. Now, if you believe that, that sort of suggests rather naturally what the generalization to ADS5 cross S5 could be. Because you see, for ADS5 cross S5, you would expect you would need the twistor space description of the four-dimensional boundary, or the ambitwistor description of ADS5 cross S5. Of ADS5. And when you look at that, and this goes de facto back already to older work of Berkovits, I mean, he proposed that the twistor theory should be written in something which he didn't call symplectic bosons and free fermions, but if you look at what he's done, that's really what they are. And in his description, there were additional fields, and he didn't have spectral flow, so the theory was somewhat different, but the ingredients were rather similar. And what's striking is that these free fields, they generate U2,2/4. And then if you remove again a U1, just like as before, you get to PSU 2,2/4, which is the global conformal symmetry of n equals to 4 superconformal Young-Mills. So you seem to be landing on your feet. Just like, incidentally, PSU 1,1/2 is just the n equals to 4 symmetry of the conformal field theory together with the R symmetry of the SU2. So what we propose is that we should consider the worldsheet theory where we have 8 symplectic bosons and 8 fermions. We don't have a T4 anymore. So basically the T4 gets replaced by another set of 4 symplectic bosons and 4 free fermions. So they basically looks exactly like what we had before. So everything is doubled. So we have 2 sets of symplectic bosons, and now we have 4 sets of fermions. And as I mentioned before, this looks exactly like what Berkovits had proposed in 2004. So you have 2 pairs of these, and then you have 4 of these. And this is what we take to be our worldsheet theory. And as it's not difficult to convince yourself, if you look at the bilinears of them, where you combine one of these and one of these, then you produce U2,2/4. And then if you divide out by this U1 field, you produce the PSU 2,2/4. And in fact, This is really just the affinization of what's called the oscillator construction of PSU2,2/4 that enters into the spin chain description of n equals to 4 super Yang-Mills. So this is again making contact with stuff people have seen in another context of describing describing n equals to 4 super Yang-Mills, namely in terms of this spin chain description that exhibits the integrability structure that's underlying this. Okay, so now I think the new ingredient that we added to this story is that, first of all, we don't add any additional gauge fields like Berkowitz did, but maybe more importantly, we expect this theory also to have spectral flow, just like the ADS3 theory had. Now, in the ADS3 theory, while I didn't say it explicitly, the way which modes get moved upwards and downwards is basically determined by the eigenvalue of J30 minus K30, where J3 and K3 are the Cartan generators of the SL2 factor and the SU2 factor. So the natural analog for ADS5 is that you take the corresponding, the J30 becomes the conformal dimension in target space. So here we take the dilatation operator, which becomes the conformal dimension in n equals to 4 super Yang-Mills. And K30 is a certain R-symmetry generator, so we replace it by some R-symmetry generator of the SU form. And that leads to the proposal that the spectrally flowed sectors should have that structure, that you should spectrally flow these symplectic bosons and fermions as written here. And then we do exactly the same as we did for ADS3. So we start with some representation. In this case, let's start with the Navier-Schwarz sector representation. It doesn't really matter, but it's slightly more convenient to describe it that way. And then as before, you see this relation. As I said before, you think of this as being the standard way to act on the Navier-Schwarz sector vacuum. So these modes kill it if R is a half or bigger. So this means that these modes kill it if the mode number is W plus 1 or bigger. So you find that these modes will kill the ground state if R is greater than W plus 1 over 2. These for the fields that have a plus sign here. And for those that have a minus sign, they behave exactly the opposite. So for them, they annihilate the ground state provided R is greater than minus W minus 1. Okay, so these are the fields that kill, but because it's a free field theory, everybody that doesn't kill creates. It's a Fock space. There's nothing fancy happening here. So if these modes kill, all the other modes don't kill. So what are the modes that don't kill? Well, from the first line, you get everybody where R is greater than W minus 1 over 2. So, sorry, R is less than W minus 1 over 2. And from the second line, you get everybody that where R is less or equal than minus W plus 1 over 2. So I can say that the first line contributes inside this wedge, and then everybody contributes if the mode number is less than minus W plus 1 over 2. So this is simply the Fock space description of the spectrally flowed representation written in terms of these free fields. Now, unlike the situation in the Berkowitz-Vafa-Witten story for PSU1,1/2 or ADS3/3, they had constructed for you a cohomology, and you knew, at least in principle, how you would determine the physical spectrum. Here, we are a little bit on our own. We've just guessed a worldsheet theory, and we have yet to define the cohomology that will characterize the physical states. And we are working on that, but this is likely to be not an entirely trivial problem, but you can guess maybe what the answer will amount to. So our guess is, and this is a postulate at that stage, that the physical state condition will amount to imposing something like an n equals to 4 critical string condition, and that its effect will be that all of the modes that are what we call out of the wedge, where the mode number is sufficiently negative, are unphysical. This is, basically you have twice as many gauge constraints, so this will remove 8 plus 8, 8 fermions plus 8 bosons. So it's plausible that this will remove all of these degrees of freedom. And we propose that all of the modes that are sufficiently negative get removed. So that only leaves you with this finite set of modes. And the finite set of modes you want to think of as being some sort of generalized zero modes. So instead of having a copy from the left and having a copy from the right separately, what we furthermore propose is that you only keep one copy from them, because they're somehow like zero modes that are shared between left movers and right movers. And that's a little bit inspired by this flux vacuum solutions, which were studied for this Berkowitz theory in these two papers in particular. But I should be honest with you. This is a very much a postulate at this stage. We would very much like to derive it from first principles. But I think our attitude is, since this leads to the right answer, there must be a way of finding a cohomology that will reproduce that, and that will be the correct cohomology to describe our string background that will be due to 3 n equals to 4 super mills. Okay, so we're not entirely done yet. So we throw away all of these out of the wedge modes. We keep the wedge modes, and then we have to impose residual gauge conditions. So one residual gauge condition is pretty obvious. You see this U1 condition we've sort of forgotten along the way. So we still have to impose this U1 condition. So remember, this comes from the U1 you have to divide out by in order to go really to PSU1, PSU2,2/4 rather than U2,2/4. So we still have to impose that. And then you would expect there's going to be some sort of Virasoro condition. And what we postulate is that the correct version of the Virasoro condition takes this form, that L0 doesn't necessarily have to be 0. It just has to be a multiple of W in the W cyclotwisted sector, and in the W spectrally flowed sector, and that you can motivate by analogy with the BMN limit and so on, but I don't want to go into that in any detail. Now, again, this is a postulate. We have no direct way of deriving this from first principles, but in our opinion, this is a very plausible postulate. And once you accept this postulate, then we can just ask what space of states do you produce? And what we can show, and I'll just sketch for you the argument in the following, the resulting spectrum reproduces then exactly that of 3 n equals to 4 supermills in the planar limit. Now, maybe you say a free theory is not that tricky, but if you actually look at the spectrum of 3 supermills in the planar limit, even that is not entirely trivial. So this is already a somewhat non-trivial statement that you reproduce that part of the spectrum. So how do you see that this really works out? Well, the smartest way of doing this is so remember, we have these wedge modes. So let's call these wedge modes collectively Zi with R running in this wedge. Then you want to think of them as being the momentum modes whose Fourier transform would give you position modes associated to the corresponding field. And because you have W momentum modes, you're going to have W position modes. So this begins to look like a spin chain with W sides, and at each side you can put one of these Zs. And in fact, if you do this and you just follow the commutation relations, then these position modes sitting at different sides pairwise commute. So this really looks like a localized spin chain where at any spin side you have the degrees of freedom coming from the Zi's and the Yi's. Now then the residual gauge conditions, if you also Fourier transform them, what they imply is that you can either impose this in sort of momentum space, or if you transform them into position space, what this implies is that at each side you impose the condition that C is equal to 0. So at each side you have the Y's and the Z's. They generate you a copy of U1,2,2/4, and then you impose the Z condition, the C condition, and that basically imposes that you're really working with PSU2,2/4. And in fact, if you go through it, what you find is that at each side you will keep the so-called singleton representation of PSU2,2/4. That's a certain infinite dimensional representation of PSU2,2/4. And then the Virasoro condition, if you look at it, what it implies is that you get that these, so you have W sides, at each of them you have a copy of the singleton representation, and then the Virasoro constraint simply forces that this W-fold tensor product of the singleton representation has to be invariant under the cyclic transformation. So what this means is you keep the cyclicity invariant piece of the W-fold tensor product of the singleton representation of PSU2,2/4. And that is a fact that has been known before. That is exactly the spectrum of 3 n equals to 4 supermills. And the dictionary that you have in mind is, you see, in 3 n equals to 4 supermills, you take any of the fields that live in your n equals to 4 supermills, and then you look at single trace vertex operators. So you have you can put W things into the trace. Each of these W things is one out of this list. This list is basically in one-to-one correspondence with the singleton representation. So you get W copies of the singleton representation, and because it's in the trace, it must be cyclically invariant. So if you count all the states that live in the W-fold tensor product of the singleton representation that are invariant in the cyclic transformation, you reproduce exactly the 3 supermill spectrum, and they match exactly with the states, the physical states that survive in the W spectrum flowed sector of our proposed worldsheet theory. So this looks very much like a string picture where the string really looks like a spin chain with W sides. At each of these sides, you have these twistor-valued string bits, and the physical state conditions just guarantee that you keep cyclically invariant piece, and thereby reproduce manifestly the spectrum of free n equals to 4 supernumerals. So this is obviously, there are gaps along the way. We don't have a first principle derivation of why exactly this is the physical spectrum, but quite remarkably, it is my opinion, if you impose what looks like fairly natural constraints, you reproduce exactly the spectrum of free n equals to 4 supermills. So we are very optimistic that we are on the right track towards finding the worldsheet theory that's really dual to free n equals to 4 supermills. So since my time is, actually I don't exactly know when I started, but I think my time is more or less up. So let me conclude. So I think for the case of ADS3 cross S3, we understand things in great detail. There is a free field realization on the worldsheet. We've really shown that it matches exactly all the structure that you expect from the symmetric orbifold theory. There we have a very concrete understanding of how this goes. And given how this fits together, there is a very natural generalization of this that you could believe should be the right description for ADS5 plus S5. And it consists of basically doubling these symplectic bosons and free fermions that appear in this free field realization. And then with some assumptions about the structure of the physical state condition that we haven't yet derived, that sort of somebody, maybe us, has to redo Berkowitz-Waffen-Witten in this more general context. We have managed to reproduce exactly the correct single trace spectrum of free n equals to 4 supermills from our worldsheet model. And this at least has a chance to open the door for the proving the ADS-CFT correspondence. I think this is closer than anybody has managed to get before, writing down a string theory that has even remotely a chance to describe n equals to 4 supermills. I think our theory has a very good chance to do so, and we see pieces of it working. Now, obviously, there's a very long list of things one needs to understand. So first and foremost, we have to understand this physical state condition from first principles. Then we would like to study the correlation functions of ADS5. That would allow you to go away from the free point. But given the fact that, remember, in ADS3, it all hinged on this incidence relation, and here it doesn't look that different. So you would expect that there is some covering map type structure that will constrain the correlation functions. And then once one's managed to do that, then one may hope that one can analyze the perturbation theory away from the free case and show that you don't just reproduce the spin chain of free n equals to 4 supermills, but you also reproduce correctly the interactions that you have to put in order to really describe n equals to 4. Now then, secretly in the background, there's some sort of higher spin symmetry that we haven't really utilized in any explicit way, but that should be there. We know there's a Youngian symmetry from the integrability perspective, so somehow that should also manifest itself from the worldsheet viewpoint. And I think that would be very interesting to understand, because that will probably also help you how to show that this really reproduces the spin chain answer. I mean, at the end of the day, you would expect that, say, the correlation functions and the perturbation analysis, the way it will work is that it will just manifestly reproduce the spin chain result. That's what you would expect this worldsheet theory to do. And then, because the spin chain reproduces correctly n equals to 4 supermills, you'll basically be done. If you can show that this worldsheet theory really conspires to just reproduce the spin chain. Now, then there are some other maybe less important points. So it gives you a slightly new view on the spectrum of n equals to 4. It looks a little bit like these variables that appear in the hexagon approach to calculating the correlator. So there are some similarities to other approaches that have appeared. But I think the key will be to really try to understand exactly how these correlation functions work and see that you really reproduce the spin chain from this worldsheet description. But then you would have an honest string theory that reproduces the correct spectrum and structure of n equals to 4 supermills. And I think that would be a very good starting point to assessing all sorts of aspects of the ADS-CFT correspondence. So I'll stop here and thank you for your attention.
Very much. Questions? Yeah, I have questions. So I remember that the hybrid formalisms contains in chiral bosons, rho, actually, it was playing a quite important role Does it play the same role, some role also in your analysis? I remember this chiral boson was very problematic when you try to do high loop computations because it creates some physical poles in the calculations. Does it play some roles here also in your analysis?
Well, I mean, for ADS3, it surely does. I mean, for ADS3, we are purely in the world of Berkowitz-Waffle-Witten. So we have the rho field and the sigma field, and as well as the PSU sector. And the PSU sector we've also described in terms of free fields, but these ghosts are definitely there, and they're there to describe the cohomology. In fact, that's in some sense what we are trying to do in understanding how to describe correctly the physical state condition from first principles. The question is, what sort of ghost fields will you have to introduce for ADS5 cross S5? What are the cohomology operators you have to define, and how will this generalize the ADS3 case?
I also remember that in the Berkowitz ADS5 cross S5 twister theory also contains some other sector, not only the Z and Y field, but there are other sectors.
Absolutely, yes. So this doesn't appear for us. So what he did, he had the Zs and the Ys, and then he put in this current algebra of C equals to 26. That doesn't, and he believed that that's how the gauge symmetry would emerge. But then he didn't have any, he put in something else, and he didn't have any spectrally fluid sectors. In our theory, there is no additional sector. Everything comes from the symplectic bosons and the fermions, but they become, or from this PSU2,2/4 sector, but they become more interesting because of the spectral flow. So they generate all the degrees of freedom coming from the spectrally flowed representations. And I mean, they're effectively topological, which is the reason why all of these out of the wedge modes disappear. I mean, in some sense, that just tells you that all of it just comes from this spectral flow. And so in our description, there's no additional degrees of freedom except for ghost fields of the kind, of the rho kind and the sigma kind. But everything else just comes from these free fields that underlie the PSU2,2/4 theory, together with its spectrally flowed representations.
Thank you.
There was a question from the Zoom. Volker.
Thank you. Hi, Matthias. Thanks for the nice talk. So actually, we played with this similar things, mostly motivated by Nathan's work some 10 years ago, and noticed that we could embed sort of the spectrum into these wedge modes. At the time, I thought to kind of remove these other modes by interpreting the model as a fully gauged Versomino model, so that only sort of these spectrally flowed wedge modes would stay in the spectrum. Do you have any thoughts on this?
Well,
so this would be sort of a mechanism to remove all the other modes by some kind of concrete BRST operator, I would say.
Well, so I think we come from sort of what we've seen to work explicitly for ADS3 cross S3. So for ADS3 cross S3, it all came just from the physical state condition a la Berkowitz-Waffle-Witten, and you didn't have to gauge by some global symmetry. I mean,
as you pointed out, it's sort of very special because lots of many of these degrees of freedoms were removed already, right?
Well, but I mean, here it's the same thing, right? Because I mean, once you've introduced the symplectic bosons and fermions, also for PSU2,2/4, I mean, this is again a level 1 theory. So again, many of these things are already, I mean, it's much smaller than a generic PSU2,2/, because you're sitting at level 1. So there it's very special. And I think that will mirror very, very naturally what happened for ADS3 cross S3. So given our experience with what happened for ADS3 cross S3, we don't see any need for this, for gauging some global group. And we expect it will rather come from, you see, I mean, you would expect this theory to be more supersymmetric than the Berkowitz-Waffle-Witten theory. I mean, the Berkowitz-Waffle-Witten theory has an n equals to 2 algebra that commutes with the PSU 1,1/2. But here, basically, your theory is double as symmetric. So it doesn't strike us as being implausible that there will be an n equals to 4 algebra that will commute with the PSU 2,2/4. And then the n equals, if you imply the physical state condition of an n equals to 4 algebra, that just will kill all the degrees of freedom. And then you just have to be careful what are zero modes and what are non-zero modes. So that's the way we believe this will pan out. And we feel that's the natural, I mean, I think different to your situation, I think by now we really understand the ADS3 cross S3 case in great detail. We really see exactly how it works. And that suggests a quite natural generalization to ADS5 cross S5. And I don't really see why it should work any differently than in ADS3 cross S3.
Okay, yeah, as you say, I mean, we didn't have, of course, all this work of yours in ADS3, so we were mostly motivated by Nathan's work. I see. This is interesting. So can you say a few words on correlation function? Because I remember that we also played trying to reconstruct big constructions. So I would be very interested.
But I mean, this is this slide, which is I mean, it doesn't do this total justice, but this is a very remarkable fact about this correlation function. It hinges exactly on defining the vertex operators correctly. So the key point here is that the vertex operators depend on X and on Z. So how do they depend on Z and on X? Actually, maybe I should add a slide so I can explain this a little bit. So you know, I mean, a vertex operator as a function of Z, you know how you describe the dependence on Z. You simply describe it by conjugation by the translation operator. L-1 is the translation operator on the world sheet. Now, if you want to, these vertex operators also depend on a space-time coordinate, which you should if you want to calculate space-time correlators, then you should modify this by also translating it in space-time. But you know what the translation operator is in space-time, and in terms of this language, it's just xj plus, and then it's e to the minus xj, and then it's 0, 0. So this is basically canonical because, I mean, you have a vertex operator at some position and you translate it by the translation operator in space-time and on the world sheet, and these two things commute with one another, so there's no ambiguity in how you define it. But this has enormous consequences for how the spectrally flowed representations behave. Because you see, when you bring, say, J minus close to this field, because J minus doesn't commute with e to the xj plus, you generate a term that will go like x squared times the piece that go like j plus. And if j plus has a pole and j minus has a 0, then j minus will acquire a pole, but it'll go proportional to x squared. So once you take this in, you can actually derive ward identities that characterize the correlators of the spectrally flowed the vertex operators. And that's what we did in this paper together with Lawrence. So we studied the SL2R ward identities. And then from these ward identities, you can show, well, actually, we could only show it ultimately in the free field case, but you can show that you get very stringent constraints on the spectrally flowed vertex operators, and the X and the Z variables get intimately linked together. And as a consequence, what turns out is that these correlators are actually proportional to delta functions in that. So for example, when you look at a 4-point function with all W's being equal, then you can obviously choose the 3 X's and 3 Z's to map into one another under the Möbius transformation. And then the correlator will only be non-zero if the 4th Z gets mapped to the 4th X. So it will be, strictly speaking, proportional to a delta function. And then if you integrate them over the world sheet, you'll really just pick out the one point in moduli space where the holomorphic covering map exists, and you reproduce exactly the map of the covering. So this is really an honest derivation of this spectrally flowed vertex operators, but it comes from being very clear about how to define these vertex operators. Now, in the case of ADS5 plus S5, you would think that something very similar will happen because you see the ingredients are exactly all the same. I mean, you have the same symplectic bosons. So in terms of these free fields, you get this sort of relation. Now we're going to get a number of relations of that kind. And what we are currently struggling a little bit with is to understand exactly what's the correct function, what are the correct covering maps. I mean, there must be covering maps, there must be maps from CP1 into CP3 with certain properties, and we are trying to count them and understand how localized they are. But we believe there's an interesting story here, and we're pretty confident there will be some delta function localization. And our suspicion is that that will just reduce this correlator basically to a spin chain calculation. That's sort of what ultimately will happen. Because I mean, this world sheet theory just wants to be a spin chain description. It's sort of the stringy version of it. And this delta function type behavior is the sort of thing that will localize it to something that looks like a discrete spin chain. So that's something we are currently working on, but we haven't quite, we're still struggling a little bit with the algebraic geometry and the exactly of what characterizes these holomorphic maps and so on. So we are not quite there yet. So this is what I'm referring to here.
Thanks a lot. Yeah.
Okay, thank you. Other questions? Can you say something about the perturbations in the ADS3 case?
That's a very good question. So that's also something we are trying to do at the moment. So in the ADS3 case, you know what you have to do, right? In the ADS3 case, there's one interesting vertex operator that deforms the symmetric orbifold away from the symmetric orbifold point. That's the two-cycle twisted sector exactly marginal operator. Now, because we have this dictionary, we know exactly which vertex operator on the world sheet it corresponds to. So therefore, the perturbation theory of your symmetric orbifold should be reproduced by perturbing your world sheet theory by that very specific physical vertex operator. And because we have these correlation functions under control, they are just labeled by these delta function localized covering maps, we should be able to work this out and reproduce the correct structure of the perturbation theory that people have calculated for the symmetric orbifold. Now, it's technically a little bit difficult because the perturbing field is not a ground state, it's a symplectic boson descendant. So you have to wrap the symplectic boson mode in some complicated fashion and so on. So we are still struggling a little bit with the technicalities, but I think all the ingredients are there, and it's just a matter of sitting down and doing it to show that this reproduces correctly the perturbation theory of the symmetric orbifold away from the symmetric orbifold point. And this is sort of the toy model calculation that we hope will then also generalize in a very similar manner to ADS5, but obviously there we are further away yet.
Okay. If there are no other urgent questions, let us thank Matthias one more time for his talk. And we break for lunch, and we have one more talk after lunch by Volker. So we come back when at 3:30 again. So back at 3:30. Thank you, Matthias.